Hey everyone, so this is the recordings of the on-demand part for APSC 172. These are the topics that I plan to cover. Of course, CourseCram will have a table of values set up for you, and you can click on the links in the table of values. It will be very done super pro. Just a quick introduction to say that these are the topics that I plan to cover. You see 2 stars here because those 2 questions have been asked the most on the past finals that I've seen. Now I am going to cover all of those, basically all of those topics. I have a document prepared where I copied the questions beforehand. If I make a typo and I don't see it right away, I want to apologize right away. I'm human, so please let me know if you want. Don't let it, destroy your faith in mathematics of some kind or something. If you have any questions, you could always email me. My email that you all know already, but just in case, is antoine@prep101.com. And we begin with those topics one after the others. The topics are obviously not all recorded in the same time frame, so I might have sometime today, sometime tomorrow, so you'll see me change outfits and stuff. Sometimes I'll say I'm gonna pause a video to take a small break, or to copy a question, or to check something. So again, I'm trying to do this as clearly and as straightforward as possible. As always, if you have any questions or comments, then I always welcome them at antoine@prep101.com. So thank you very much, and let's begin with our topics. In this question, we begin with the slope of a path. And I remind you that when we have a path, R of t, so when we have a path, R of t, that path will be made up of an x of t, a y of t, and a z of t. So the slope of our path, m, is given to us by how fast we are moving vertically, so z prime, where it's the vertical speed, all divided by the horizontal speed, which is the square root of x prime squared plus y prime squared. This is the magnitude, by the way, of the vector x prime, y prime, so the speed, but only in the x and y plane, right? So this would be the magnitude of the vector that's x prime, y prime, basically the velocity vector, but in the xy plane. So this is the vertical speed divided by the speed in the xy plane, and that gives us how fast the particle is moving up. So how fast is moving up when it moves 1 unit in the xy plane, we get the actual slope increasing or decreasing. So a bug crawls on the plane. This is again from 2021. So a bug crawls on the plane from this point to this point, along a path whose projection down in the xy plane is this parabola. So what we see in the plane, the bug is just going on the path on top. What we see in the plane is the parabola y equals to x squared. Note that this is important. X goes from -2 to 2. So that gives us the range that we're going to use for t in a second. So we want to find at which point the path is most steep or least steep, where steepness is measured as the absolute value of the slope. So we don't care if it's going up or if it's going down. What we really care about is how steep is it. So the minimum value would be, steepness 0, and the maximum value is, again, we don't care if it's plus or minus, would be the maximum of the absolute value of m, which they say right here. So again, we don't care if it's positive or negative. What we really care about is that how steep that path is. So as a first, in part A, they're asking us to provide a technical analysis. So basically find the maximum and minimum of the slope of this of the path of this bug. Now first thing you want to do is you want to come up with R of t. So you want to find the equation of that path, and R of t is set up for you. It's the intersection between this and this. So because x has the range, so it's beneficial to us to make x is equal to t. Then since y equals to t squared, y equals to x squared, then x is equal to t squared. And then z is 2x plus y, so basically z, sorry, I am gonna just shut down my notifications. Here we go. So z is equal to 2x plus y, so 2x plus y. Now, since x goes from minus 2 to 2, as I said, this gives us an easy way to give the range for t. T goes from minus 2 to 2. So basically our r of t, our path, is t squared and 2t plus t squared. You can write it like this, as a path r of t with an x and a y and a z, or you could just simply not use r of t. You could just simply say the path is t squared and t squared and 2t plus t squared, where this is the position x, this is the position y, and this is the position t. So either way it's the same thing. So we would like to find the slope. So x prime, that's 1, y prime is 2t, z prime is 2 plus 2t. So the slope of the path is, at any point, z prime, 2 plus 2t divided by the square root of 1 squared is 1, 2t squared is 2t. Now, we want to maximize, right? We want to maximize or minimize. We don't care either way. I'm sorry, I should be clear. We want to maximize the absolute value of m. Excuse me. So we want to find where the slope is the steepest. Rather, we don't care if it's plus or minus, as I said before. And the minimum is technically when this is equal to 0, right? Like if you want to find the maximum of absolute value of m, there is some work to be done, but the minimum of absolute value of m, that's the minimum of the absolute value of 2 plus 2t over the square. The square root is anyway positive, so you don't need to put an absolute value on it. And the minimum of this is when 2 plus 2t is equal to 0, therefore when t equals to minus 1. Right? You don't, because this is an absolute value. This is always going to be positive values. So the smallest of the positive values is when this is equal to 0, right? So the minimum of this is when it's equal to 0. And that's equal to 0 when the top is 0, and the top is 0 when t equals to 1. So for maximization, we're going to use calculus, right? So we're going to find the derivative, we're going to set it equal to 0, and that's what's going to give us the maximum. Again, we don't care if it's a max or a min, because when we put an absolute value on it, this is going to give us the steepest slope, right? We don't care if it's the max or a min, because when you put in an absolute value on it, it'll just be the point where it's the most steep. Another way of doing this is you can maximize m squared. I think this is what your teachers use. I can't remember. I read this solution a while back. So you can maximize m squared. So if you don't care whether it's positive or negative, you just want the maximum of n. So maximize m squared. So that way, whether it's a negative or positive value, is just always going to give you the steepest thing. We can go from here. We can find m prime as a function of t. Now, I like the idea of maximizing m squared because it gets rid of the root. So if we find that this gets too complicated, we're just going to switch and do maximization of m squared. But let's start first with the most natural way. You have a function m of t, and you want to find at what point do you get the maximum of this function. So the derivative of the top times the bottom minus the top times the derivative of the bottom, which is 8t over 2 the square root of 1 plus 4t squared, all divided by the bottom squared, so 1 plus 4t squared, all not squared because that's already squared. Okay, so it's not super bad. You can create a square root, you can create a common denominator on top, the square root of 1 plus 4t squared. So I'm creating a common denominator on top. Of course, that 2 cancel that with that 8 and that becomes 4. So that gives me 2 times 1 plus 4t squared minus 4t times 2 plus 2t. And we know that to achieve a maximum or a minimum, we need to set the derivative equal to 0. And we know that a fraction is equal to 0 if the top part is equal to 0. So that would be 2 plus 8t squared minus 8t minus 8t squared is equal to 0. Those cancel out, so we get 8t is equal to 2, so t is equal to 1 over 4. Now, again, whether it's a max or a min, we don't care because we're looking for the steepest, whether going up or going down. So we're going to get the maximum. Let's look at the question. What did they ask for it? Find the maximum and minimum. So the maximum of the absolute value of m is at t equals to 1 over 4. And the minimum of the absolute value of m is at t equals to minus 1. Of course, those give us points, right? So they say provide the maximum. They don't tell us find the points, but if you wanted to find the points, you plug those into x, y, z, right? So x is t, y is t squared, and z is 2t plus t squared. So 2t plus t squared, whatever that is. And here you get the point x, y, z is equal to x is t, y is t squared, and z is 2t plus t squared. So 2 times t plus t squared. Right, so those are the 2 points where we get a maximum or a minimum. So I'm adding a page to continue. Since I have the option, I just like my pages a little colored, so here we go. So that answers part A. Now, part B, I honestly had to read a couple of times part B to see what they mean. Explain how your solution could be obtained with a careful examination of the interaction between the bog's path and the contour lines of the plane. Remember, the bog is on this plane, and then when we get z equals to a constant, we are going to get contour lines. So how do the contour lines tell us that we did a good job finding the maximum and the minimum? So let's write this down for a second. So z is equal to 2x plus y. Now if z is equal to a constant, right, because we're going to get level curves, that means we have y is equal to minus 2x. Let's make the constant k, let's say. So z is equal to minus 2x plus k. So these are the contour lines. So let's do a kind of a rudimentary graph here. So if k is equal to 0, we're going to get y equals minus 2x. So like this. You know what? Since we know what's going to happens at x equals to minus 1, right? And x is equal to 1 over 4. So let's draw those contour lines. So this is the contour line where k is equal to 0. So if I make x is equal to minus 1 here, x is equal to minus 1, let's say, that means y is equal to, well, let's draw a contour line that goes through that. So this is the contour line where x is equal to minus 1. I don't know what k value this is, we can figure it out later. And the contour line where x is equal to 1/4, let's say, is here. should be a little bit closer. So let's say this is the contour line where x that goes through x is equal to 1/4. This is the contour line that goes through x is equal to -1. So now, so if x is equal to 1/4, let's draw the parabola. So let's say 1 is here. So -1, 1 is here. I'm gonna do the parabola in purple. So this is the parabola. The parabola should go like this. This is not a nice parabola. I'm trying to. Okay, I'll tell you why I'm hoping for tangency there. You'll see. Okay, so look, there's a reason why I drew it this way. I will tell you in a second. So we want to get the maximum slope and we want to get the minimum slope. Right. Maximum slope, that means Z changes most rapidly, correct? And minimum slope in this case, and we discussed that the minimum slope here is going to be 0. That means there's going to be no change in Z. Right? It's minimum absolute value of the slope to be specific. So it's always positive. So the steepest is when Z changes most rapidly. Again, we don't know if it's an increase most rapidly or a decrease most rapidly. And the minimum slope with the minimum absolute value of slope is when the slope is equal to 0. Now, something from directional derivatives, and we will go over that later when I cover directional derivatives, but there's something that we know. That we know that f increases most rapidly in the direction of the gradient of f, right? And if you wanted to decrease the most rapidly, then it's in the direction of minus the gradient of f. So decreases in minus the gradient and increases in the direction of the gradient. Now, the gradient is always perpendicular to the contour lines, right? The gradient is always, we know that the gradient of a function f is always perpendicular to level curves. Level curves, or another word for those level curves, is contour lines. So let's try and analyze this. Here, at the point where x is equal to -1, I was hoping for a tangent, by the way, so I'm going to adjust this line a little bit. I'm hoping to get tangent at x equals to -1. So at x equals to -1, I'm going to say here. So look, when we are at x equals to -1, the gradient is perpendicular to the level curve. So the gradient has this direction. Now, I don't know if it's going this way or it's going this way. I generally don't care in this case, because I don't care if it's increasing most rapidly or decreasing most rapidly. I care that it's changing most rapidly. So look here. At the point where t equals to -1, where t equals to -1, the bug is moving perpendicular to the gradient, because this is the movement, right? This is how the bug is moving. Movement, and this is the gradient. Because this is the movement is tangent to the level curve, right? So the y equals x squared is tangent to the level curve or the contour map. That means the movement is perpendicular to the gradient. That means we have no change in z. that means we have the slope equals to 0. If you remember that when we move perpendicular to the gradient, we get no change in the function. When we move perpendicular to the gradient, we are on a level curve, and therefore there is no change in the gradient. Now, this is to justify t equals to minus 1 or x is equal to minus 1, right? T equals to minus 1 or x is equal to minus 1 is the same thing because t is equal to x. Remember how we parameterized it here. So now, to justify the maximum at 1 over 4, if you look at 1 over 4, the gradient has this direction, right? The gradient is perpendicular to the level curve when x is equal to 1 over 4. The gradient is perpendicular to the blue line, to the level curve, which means, remember, the purple is the movement. It means when t is equal to 1 over 4, the bug is moving in the direction of either the gradient of f or minus the gradient of f. We don't know whether it's increasing or decreasing, but it's moving in the direction that's either positive the gradient or minus the gradient, right? And that tells us that we have the maximum rate of change of that. That means z changes. That means we have maximum steepness. Right, the slope is the most steep, which means we get the maximum change in z. Right, so that's the justification of this. Of course, there's plenty of examples of contour maps coming up later, and we're going to do a couple more examples on the slope of the path to make sure this sticks. So that's the first problem, which comes from 2021. It covers the slope of the path in relation with the contour maps. Right, so let's look at a problem from 2019. So this says that we have a cylinder that intersects a plane, and the first part of the question that's not right here right now, they ask us to parameterize the path. Now, if we weren't given this, my hope is that you'd be able to get this pretty easily. So how do I parameterize the path of intersection between this and this? So think about it for a second. We have x squared plus y squared is equal to 25. That means we want to take x is equal to 5 cos and y is equal to 5 sine, because then x squared plus y squared, that's 25 cos squared plus 25 y squared, which is equal to 25. And then we sub x equals 5 cos and y equals to 5 sine in this, and we get z is equal to this. And if we absolutely must write a range for t, then t is from 0 to 2 pi, because it's the whole cylinder. It's all around the cylinder. So this question refers to the curve C. This is the curve C. Find the x and y coordinates where the slope of the curve has maximum magnitude. So same idea. And calculate the magnitude of these points. So what is m? The slope, that would be z prime, so negative 5 sine t plus 10 cos t, all divided by, and if you do the square root of x prime, that's going to be minus 5 sine t all squared, y prime is 5 cos t all squared, and that simplifies very, very nicely. That gives you 25. Root of 25 is 5, so this is minus 2 sine t, actually minus sine t plus 2 cosine t. And we're examining the maximum slope. Again, positive or negative, we don't know. You get maximum m, so you get the maximum or minimum m when the derivative is equal to 0. So the derivative is minus cosine t minus 2 sine t, and you set that equal to 0, which means that gives you tangent t is equal to a half, and you have tangent t equals to a half for tangent t is equal to a half. We gotta do some trig. Where is tangent positive? Tangent positive, it's minus a half. I'm sorry, it's a good thing that we caught it. Minus a half. So tangent is negative in this quadrant, so there's a quadrant here, and tangent is negative in quadrant here. So let's call this, let's say, value t1, and let's call this value t2. So if tangent is minus 1/2, there's an easy trick to find this. So you can draw a triangle, right? Worry only about the values so far. So tangent is opposite over adjacent, which makes this √5 using simple Pythagoras. And that means you get sine t is equal to plus or minus. So in quadrant 2, when you're in quadrant 2, that's t1, so the sine is positive, so sine is opposite over hypotenuse. Cosine t1 is negative, so minus adjacent over hypotenuse. Now in quadrant 4, sine t2 would be, the sine is negative, so minus 1 over √5. You get the sine from the quadrant and the value from the triangle. And here cosine t2 is equal to 2 over √5. So this is t1 in quadrant 2, that's one solution. T2 in quadrant 4, and that's the other solution. So what do they want from us? They want the x and y coordinates of the points where the slope of the curve has maximum magnitude. Remember, x is 5 cos and y equals to 5 sine. So here the point xy, 5 cos, 5 sine, so minus 10 over √5, 5 sine, 5 over √5, and the xy here for this point is going to be 10 over √5 minus 5 over √5. Find the points where the slope, calculate the magnitude of the slope. So what is m in this case? We have m right here, right? So m is equal to, we don't know if it's plus or minus, right? So we really don't know what, so we want the magnitude of the slope. So let's take absolute value of m. And you realize whether you put t1 or t2, you're going to get the same thing. So this is going to be the absolute value of minus sine, so minus 1 over √5, plus 2 cosine, so minus 4 over √5. And in absolute value, you have minus minus, so it doesn't matter if, you know, when you take the absolute value of this, this is just going to be 1 over √5 plus 4 over √5, which is 5 over √5, which is √5. Again, we don't know if this is the absolute value of m. So at one of these points, probably the maximum slope is going up, and then at the other point, the slope is going down. But either way, this is the maximum slope that we get, and the points are here. Now, the mistake is probably here. Some will try and solve for t and get like a decimal number. You can, but it might make working these points a little bit longer. My trick is, I will say it again, the triangle is used to get the values, and the quadrant, so the triangle gives us the values, and the quadrants give us the sign. So I know that t1 is in quadrant 2, that means its sine is positive, its cosine is negative, and I know that t2 is in quadrant 4, so its sine is negative, its cosine is positive. Right, so this is a trigonometry trick that I hope you will find useful. So that's another example of a problem that has of a problem about the slope of a path. So the next topic I want to talk to you about is the gradient and how it connects to level curves and level surfaces. So let's see, if I have a function f(x,y), right, z is equal to f(x,y), let's say, its graph would be a surface. A graph would be in R3, and therefore the graph would be a surface. Now, if I take the gradient of f, and I'm sure everybody knows that the gradient of f is f sub x, f sub y in this case, that gives me a vector. This vector will be perpendicular to the level curves of this surface. What are level curves? When I take a z or f, they're the same thing, is equal to a constant. So when I make the function equal to a fixed constant, that makes it lose a dimension. So it drops from R3 to R2, and that becomes a level curve. Right, in R2 we have curves, in R3 we have surfaces. So now, we definitely, for each value of k, we have a different level curve or contour line, and different contour lines make up a contour map. So here we have a level curve, and all of these level curves become a contour line later on, a contour map later on. So what we know that, and by the way, you've definitely seen level curves, right? Especially in 172, we covered them extensively. Like there'd be like stuff like this, and z increases or decreases or whatever. So the gradient, our magnificent gradient, the gradient of f will be perpendicular to perpendicular to the level curves for any k. So it's just perpendicular to any level curve. So at any point, at all points. So let's say this would be our level curve, and you want to find the gradient at this point. Then the gradient would have this direction. Like it would be perpendicular to the level curve. Now, does it go that way or does it go that way? This is an addition that we learned from the directional derivatives, that it's perpendicular to the level curve in the direction of increasing f or increasing z. Remember, when we move in the direction of the gradient, our function increases most rapidly. And when we move opposite to the gradient, our function decreases most rapidly. So when we move either in the direction of the gradient or opposite to the gradient, our function is either increasing or decreasing most rapidly. So we have the maximum change in the function, right? So here the gradient is always perpendicular to the level curve at any given point, and it points in the direction of the increasing z. Now, if we have a function w equals to f of x, y, z, now its graph, that would be in R4, so we can't really see its graph, it's some kind of hypersurface. Now, when we set f, x, y, z equals to a constant, it'll drop a dimension, and that makes it in R3, which makes it a level surface. Now, when I take the gradient of f here, the gradient of f, which would be f sub x, f sub y, and f sub z, the gradient vector is perpendicular to the level surface at any point. Again, in the direction of increasing t, but what we care most about this is that it's perpendicular to the level surface. So if we have a surface like this, let's say, and you want to find at this point P, you want to find the direction of the gradient. The direction of the gradient is like this. So this is the gradient, let's make it in red. This is the gradient of f, let's say. Of course, it could be the other way around. And this is perpendicular to the level surface. Now, why do we care about this? Because In this case, the gradient, see in this case, and we're going to do this later, in this case, which is a very important case, the gradient of f, is perpendicular to the tangent plane. So we use the gradient of f to be the direction, to be the normal, the vector that's perpendicular to the tangent plane. And then when we talk about tangent planes in just a bit, we're gonna do exactly that. Right, so again, the gradient is perpendicular to the level surface at any point. The gradient is perpendicular to the level curve at any point. When we want to use tangent planes, we use the gradient as normal vector. That's about it for now. So I want to go to the first practice problem. So we want to find the tangent to the path of intersection of two surfaces. It's another question that comes out often. So let's talk about this. So we have this curve, we have this surface, and we have this surface. Now let me just take a step back and talk about these surfaces. How do I know that this is a surface? Okay, how do I know that this is a surface? Well, I can write this as zx minus x squared minus y squared is equal to 0. So this is like here, I have a function f x y z equals to 0. Right, so this is a level surface of f. And this one, I make z cubed minus 4x squared minus 4y cubed equals to 0. And I'm going to call this the function gxyz, and that becomes a level surface of G. So we have now two level surfaces. And as I said in the session for the midterms, always, anytime you have, let's say, like some function f of x, anytime you have an equation where you have like a bunch of things equal to a bunch of things equation in x, y, z, you could just always move this to here, and you got yourself a level surface or a level curve. So you can always get a level surface or a level curve by just moving everything to one side. And if it's a function of only x, y, then it's a level curve. And if it's a function of x, y, z, then it's a level surface, right? Because we talked about it here. If it's a function of x, y equal to a constant, then it's a level curve. And if it's a function of x, y, z equal to a constant, then it's a level surface. All right, so let's get to the problem. So we have the intersection of two level surfaces, and we want to find the parametric equations, so which means x of t, y of t, z of t, of the line that is tangent to C. So the line that is tangent to the level curve. We have the point. Okay, so let's start from the beginning. If we want to find the parametric equations of a line, so if we want to find the parametric equations of a line, basically we want to find the direction times t plus the point. That's how we find parametric equations of a line. Direction times t plus point. Now the point we have, the point is 1, 1, 2. Great. What is the direction? So we have one surface intersecting another surface. So here's the intersection, right? So we have a curve C like this. We have a tangent at the curve. So if I make, like, see, this is the surface, this is the line that is tangent to the surface, and I want to find the direction of that line. Okay, so it's a line again that's tangent to the curve of the intersection, right? So if we think about it for a couple of seconds, we see that gradients are extremely useful in this case, right? Gradients are extremely useful in this case. Why? Because the gradient of f, which is equal to let's find the gradient here. Derivative with respect to x, that would be z minus 2x. Derivative with respect to y is minus 2y. Derivative with respect to z is x. This gradient vector, of course, at the point 1, 1, 2, the gradient of f is equal to z minus 2x minus 2y and x. This is perpendicular to C, right? C is in the level surface F, and C is in the level surface of G. C is in both level surfaces because C is the intersection of the level surfaces. So if C is in the level surface of F, that means since the gradient of F is perpendicular to the level surface, then in particular it's perpendicular to C. Now, by the same idea, the gradient of G is equal to the derivative with respect to x is minus 8x, the derivative with respect to y is minus 12y, the derivative with respect to z is 3z squared. Of course, sorry about the y squared. So at 1, 1, 2, the gradient of G is going to be minus 8, minus 12, and 12. Right? The gradient of G is also perpendicular to C. Let me say that again. C is in this level surface, and since the gradient of F is perpendicular to the level surface and C is in the level surface, that means the gradient of F is perpendicular to C. Of course, all of this is happening at the point 1, 1, 2. By the same idea, C belongs to this level surface. C belongs to this level surface. Therefore, since the gradient of G is perpendicular to this level surface, in particular, it's perpendicular to C, again, at the point 1, 1, 2. So, the direction that C is going, which is the direction of the tangent, right? So, the tangent will have the same direction as C. What's the direction of C? If C is perpendicular to two vectors, so what's the direction that is perpendicular to two vectors? Therefore, the tangent to C at the point 1, 1, 2 has direction gradient of F cross the gradient of G, right? So the cross product is the vector that is perpendicular to those. Gradient of F cross gradient of G is a vector that is perpendicular to both the gradient of F and the gradient of G. Now that is if you've done the cross product, right? So if you've done the cross product, then take the cross product of F by G, and then that gives you a direction that is perpendicular to both lines. Quickly, as a reminder about the cross product, I'll do this in green here. So this is a quick reminder of the cross product. Again, if you haven't done the cross product or you don't want to use it, I'll give you an alternative that's a little bit longer. The cross product only works in R3. So if I have a vector u that is u1, u2, u3, and if I have a vector v that is v1, v2, v3, the vector u cross v is perpendicular to both u and v. By the way, you could remember this using the right hand rule. So u, v, u cross v. That's the idea. This is u, this is v, this is u cross v. It's perpendicular to both vectors. So how you find it is, I'll show you a quick idea. So for the first component, you cancel this. So you do plus, minus, plus, and then plus. So for the first component, you cancel this. You find the determinant of what's left. And if you don't know what the determinant is, then you simply do u2 v3 minus v2 u3. For the second component, minus take out this, take the determinant of what's left, u1 v3 minus v1 u3, and the last component take plus, cancel this out, so u1 v2 minus v1 u2. And that gives you a vector that is perpendicular to both vectors. You could do that here to get the vector you want, which is the direction. So if you want to do it here, you cancel this, so this is minus 24 plus 12 is minus 12. Then 0 minus minus 8, that's 8. So minus, it becomes minus 8, and then cancel this, that would be 0 minus 16. And this would be the direction. Of course, if you have a direction, we could divide by minus 4. We'll get 3 to 4. Because it's a direction. Like, what does it matter if this is the direction of the line, or this is the direction of the line, or if this is the direction of the line? All of those are the same line. Therefore, the tangent would be direction t plus point. The point is 1, 1, 2. Now, if you do not want to use the cross product, let's say you don't want to use the cross product, so how do we find the solution without cross product? It's a little bit longer, but that's fine. You can say that the direction is the vector ABC, let's say. Now, and you know that ABC dot the vector 0 minus 2, 1 is equal to 0, because it's perpendicular to the gradient of f. And ABC dot minus 8 minus 12, 12 is also equal to 0, because it's perpendicular to the gradient of g. So that gives you two equations, minus 2b plus c equals to 0, and then minus 8a minus 12b plus 12c is equal to 0. So you could solve this. You can say c is equal to 2b. You replace that here, you get minus 8a minus 12b. C is 2b, so that's 24b, so equals to 0. So that means minus 8a plus 12b equals to 0. That means a is equal to 12 over 8, so 3 over 2b. So if you take b equals to 2, a will be 3, and then c will be 4. So the vector is 3, 2, 4. Well, what do you know? That's the same thing. Either way, it's doable. Either way, it's not the end of the world. You were able to find the direction of the tangent. And now, as a recap to what we're doing before, what would be the slope of the curve, right? So this is the tangent line. Right, this is the tangent line. So to do part B really quickly here, x is equal to 3t plus 1, y is equal to 2t plus 1, and z is equal to 4t plus 2. Those are the parametric equations of the tangent line. In part B, they ask us for the slope of the curve. So you know what the slope is, it's z prime. So the slope, again, we don't know if it's plus or minus. So, I don't know, say plus or minus. And then the slope is z prime over the square root of x prime squared plus y prime squared. So 9 plus 4 is 13. So it could be plus or minus 4 over the square root of 13. Right? So that's part B, the slope of the line. And that's an example of how we find the tangent line to the tangent to a parametric curve, the tangent to the curve C. Now, I want to add a note before I go. Just a quick note that the if given, so I'm not sure if you'll ever use this note or not, but in the to make everything complete. So if you have x is equal to f of t, y is equal to g of t, and z is equal to h of t. So if this gives you a path C, and if you have x of t, g of t, of y of t, that means the tangent would have direction. The tangent has direction f prime of t, the derivatives, f prime of t, g prime of t, and h prime of t. Right, so the tangent will be the direction of the tangent would be the vectors of the derivatives. Now, why didn't we use this here? Why did we go through the cross product of the level of the gradients and whatnot? Because we don't have what f of t, y of t, x of t, y of t, and z of t is. We don't know what the curve is in terms of x, y, z. Now, you say, okay, can I try and parametrize it here? Remember in the previous question here, we took, like see here, from this we took x is equal to 5 cos 5 sine, we plugged it in here, we got z. So if you can find a way to parametrize it, if you can find a way to find x of t, y of t, and z of t here, then by all means do it, but it's incredibly difficult here. So we don't know how to do it here. This is why we say that the direction of the tangent would be perpendicular to the gradient of f and the gradient of g. Therefore, it's parallel to their cross product, or just don't worry about the cross product and just find the direction by saying the direction dot the gradient of f is 0, the direction dot the gradient of g is 0, then find the direction that way. Right, so that's an example of finding the direction. Same thing here, but see here is that other example I was talking to you about. So you want to find a parametric equation for the curve. We actually did this. I told you about this before. So here the curve is the intersection of this and this, these two level surfaces. You can make them into level surfaces if you wish. But here it's easy to find f of t, g of t, and h of t, right? We saw this before. We can say x is equal to 5 cos t. We can say that y is equal to 5 sine t. And we can say z is equal to x plus 2y. So x plus 2y. And 0 t 2 pi. So here, if they say find the parametric equation for the line tangent to the curve, right? If we want to find the direction of the line that is tangent to the curve, all we have to do is say that the direction is minus 5 sine t x prime, 5 cos t, that's y prime, and minus 5 sine t plus 10 cos t. So this would be the direction that we are looking for. Right? So this would be the direction that we're looking for. The problem is that we want to find, we're saying at the point 4, 3, 10. So what is this at the point 4, 3, 10? So they make it easier one way, they make it harder the other. So what do I plug in here? What t do I plug in here to get the direction? You understand what I'm saying? So I need this. This is A, this is B, and this is C. This is the direction. That's great. But what do I plug in them to get them to be the point here? At this point, what is this vector? And it's a somewhat easy trick if you spend enough time on it. Maybe you want to pause and try and do it on your own, then you'll unpause and see what we're doing. What is this point? This point is some value of t in here, right? To get this point, you plugged in some value of t to get here. That's the same value of t that you want to plug here. But what do I mean? I mean that the 5 cos t, the x, 5 cos t, is in fact 4. There's a value of t that made 5 cos t become 4. There's a value of t that made 5 sine t 3. And there's a value of t that made 5 cos t plus 10 sine t 10. And if you think about it, 10 sine t, that's 6. 4 plus 6 is 10. See, these two, if you plug them in here, it makes all sense. But that tells you that you have cos t, right? It tells you that cos this particular t is 4 over 5, and sine this particular t is 3 over 5, and that's what you plug in here. So the direction is going to be, I'm going to stay in green so you know, this is minus 5, and sine t is 3 over 5. It's that value of t where sine t is 3 over 5. Cos t is 4 over 5. And sine t is 3 over 5. And cos t is 4 over 5. So you get the direction minus 3, 4. And that's minus 3 plus 8 is 5. And that's what you just plug in here. Again, we know that the direction is the derivative of x, y, and z. The question is, what do I plug in there? What do I put t as? So I can get like, I want the direction at the point 4, 3, 10. I don't want the direction anywhere. I want the direction of the tangent at this point. Now, at this point, that means when I plugged in some value of t in the x, y, and z, I got 4, 3, 10, which means you get these equations one more time. X is equal to 4, y is equal to 3, and z is equal to 10. You get the value of cos t and sine t, and instead of solving for t, you really don't need to. You just put in what cos t and sine t are here, and that gives you the direction of the tangent line. So we've done the direction of the tangent line when we didn't know the x and y and z, so we had to do the cross product of the gradients, and we did the direction of the tangent to a path when we knew the equations, and we need to just find the derivative. And now to other exciting topics. Let us talk now about directional derivatives. I'll explain the main idea, and there's some stuff that we said before, but I will repeat briefly. So what's the idea of the directional derivative? So it's the derivative in a certain direction. Now, derivative, I remind you, is a rate of change. So this measures the change of a function when you move, when the point moves from one location to the other, so when the point moves in a certain direction. So the formula is the directional derivative of a function f at some point p0, so you're at some point p0 and you're moving in a direction u, is equal to, and I'll tell you what this is, but first let me define those. This is the direction of the movement. You're at p0. This is the function that is changing, and this is the directional derivative, which means this is the rate of change. And by the way, if it's negative, the function is decreasing. If it's positive, the function is increasing, so on and so forth. So what is this? This is the gradient of f at point p0 dot the direction of the movement divided by the magnitude of u, which is the magnitude of the direction of the movement. Basically, we are making u, we're taking u divided by the magnitude of u to make it into a unit vector. So if you move in this direction, or in this direction, or in this direction, or in this direction, it doesn't really matter, you get the same directional derivative because you're still moving in the same direction. Now, if we use the formula for the dot product, we realize that this is the magnitude of the gradient. It's at p0. Let me just, we know that. Times the magnitude of u times cosine theta, where cosine theta is the angle between the gradient of f and the direction of the movement, divided by the magnitude of u, the length of u. Those cancel out, and we get that the directional derivative is the gradient times cosine theta, where theta is the angle between the gradient and the direction in which we move. So let's review what we said before. What happens, what's the maximum value of cosine theta? See, the maximum value of cosine theta is then when theta is equal to 0. You get the largest directional derivative of f u at p0, right? Because cosine theta would then be 1. So that means the largest, the most positive rate of change is equal to the magnitude of the gradient. And this happens when? It happens when theta is equal to 0. That means u is in the same direction of the gradient of f, right? If theta is equal to 0, that means u and the gradient, they both go in the same direction. So you get the maximum increase when you move in the direction of gradient of f. Right, what is the smallest? What's the most negative thing? This is when theta is equal to pi. This is when cosine theta is minus 1. You get the most, like the largest, but in a negative sense. And then you get the directional derivative of u of f in the direction of u is minus the gradient of f. Meaning what? Minus means it's decrease. So you get the maximum decrease, the fastest decrease, right? Your function will decrease most rapidly when you move in the direction of minus the gradient of f, because that's how you get theta equals to pi. The pi means u is opposite to the gradient. So if you want to get the maximum rate of change, if you want your function to increase or decrease most rapidly, either go in the direction of the gradient or opposite to the gradient, which is what we said in the examples that we solved earlier. Now, if you want no change in your function, right? If you want your function not to change, then take theta is equal to pi over 2, meaning cosine theta is equal to 0, which means what? That means the directional derivative at point P0 is equal to 0. That means f does not change, right? That means you move, this is when you move perpendicular to the gradient. Now, I want to say another word about this because we talked about it. What's perpendicular to the gradient? The gradient is at all times perpendicular to the level curve, right? So, or the level curve or the level surface, right? So when you move perpendicular to the gradient, it means you are on a level curve or a level surface. Now, what does it mean, level curve or level surface? It means that the function is equal to a constant, which means the function does not change. You see how it all makes sense? So if you move perpendicular to the gradient, you're basically on a level curve or a level surface, which means your function does not change. So if you want your function not to change, move perpendicular to the gradient. If you want your function to increase most rapidly, go in the direction of the gradient. If you want your function to decrease most rapidly, move in the direction opposite to the gradient. Or if you want just maximum change, either in the direction of the gradient or opposite to the gradient, you will get the maximum change, and the rate of change in that case is the magnitude of the gradient. Like the maximum rate of change, you can see, is either the gradient or minus the magnitude of the gradient. So the maximum rate of change that a function can have at a point P0 is the magnitude or the length of the gradient vector at P0. Right, so this is a small overview of directional derivative. Let's go to practice problems, and I tried to pick practice problems that we didn't do in the midterm session, so you get a new set of problems and new practice things. So this is from the final of 2020. So let f be this. We have a level surface fx, y, z is equal to 2. They gave us this is a level surface. Sorry, this is a level surface. when you have f of x, y, z is equal to this, that this defines a level surface. By the way, in this, if you isolate z, then you get this. Right? And don't we know that this is a surface? It's irrelevant to this part of the question because this is used in other parts of the question. So, I mean, you could just literally just not worry about it here. So, just literally not worry about it here. But what I'm saying is, if you have this level surface, if you solve for z, then you get z is equal to some function of y. Again, if possible, right? We can't always solve for z. Sometimes we can't. So, find the directional derivative, well, of f, right? The directional derivative of f, this needs to use the, let me actually dig up the question just to be sure that I didn't not copy parts that we need for this. So here we go. Just 1 second. I did the whole thing and I didn't open the files. 2 seconds. Right, so for this one we need the implicit function theorem. Yeah, so I copied everything we need. So for this one we need what we call the implicit function theorem. I will show you what this is. To be honest, I didn't explain that to you earlier. I will explain that to you now. And just double check if you've covered it. Covered this year. I don't remember having covered it in the midterm session, but I could be wrong. Check if this is covered this year. So let's see. We want to find, I'll tell you why we need it, and I'll explain it to you step by step, don't worry. So we want the directional derivative of f at the point 1, 0. Now notice that 1, 0 matches all of these points that we have, so that's good. So the directional derivative is the gradient of f at the point 1, 0. F is a point of x, y, z. Dot the vector u, which is 1, 2, divided by the magnitude of the vector u. So this means we need f sub x at the point 1, 0, of course, f sub y dot the vector 1, 2, all divided by the square root of 1 squared plus 2 squared. So, which is root 5. So what is f sub x and what is f sub y? And this is small f, not big F. Here is where the implicit function theorem kicks in. This is what the implicit function theorem tells you. The implicit function theorem tells you that if z, let's continue in blue. So if z is a function of xy defined by some function of x, y, z is equal to a constant. Because sometimes, as I said, you can't solve for z. So let's say you have, let's say that this level surface was x squared z plus e to the z minus 2yz is equal to 3. Right? There's no way that you could solve for z in terms of x and y. There's an e to the z here, and there's a yz here. So there's no way that you could solve for z as a function of x and y. But then this, let's say that this defines implicitly, of course, z as a function of x and y. Remember implicit differentiation, when variables are linked by an equation and we can't solve for one variable in terms of the other. So how do I find the derivative of z in this case? This is when implicit function theorem says. It says that if you want to find the derivative of z with respect to x, then what you do is you put a minus and you take the derivative of x all divided by the derivative of z of the function that defines z. And if you want to find del z, del y, then you do minus f sub y over f sub z. Again, disclaimer, I don't remember doing this in the midterm session, so please check if you've covered it this year. And if you haven't covered this year, then sorry, just skip this example. I don't want to stop the video and check and go and come back. I trust that you are fully capable of checking that. So here, minus f sub x is minus 3 over f sub z is minus 2. So that's 3 halves. And minus f sub y is minus 1 over f sub z is minus 2, which is a half. Notice how those flip here, like z is on top, it becomes on the bottom, x is on top, it becomes on the x is on the bottom, becomes on top. And this is how we find the derivative of z in terms of xy if z is defined implicitly. So here, this is implicit equation, so we can't really solve for z like something like this. This is, of course, as an example. So I can't solve for z as a function of x, y, and z, of x and y, but that doesn't mean that I can't find its derivative. And that's very simple. So here you plug 3 halves, 1 half, you dot it with 1, 2, and you divide it by root 5. So this is 1 over root 5, 3 halves plus 1, so 5 over 2 root 5. And again, some of you might be thinking, okay, if they didn't give us the implicit function theorem, then how do I solve this question? Well, very simply, if they didn't give you the implicit function theorem, then they wouldn't give you this question. The only way to do this is using the implicit function theorem. And this showed up on a final of 2020. That's why I decided to do it, just to cover all bases. Again, one last time, if this wasn't covered, then don't worry about it. You won't actually have to face this problem. We move on to other directional derivative questions. For example, this one. See here how they give you the derivatives right away. There's nothing implicit. There's nothing weird about it. So an unevenly heated plate has temperature Txy. The temperature is in degrees Celsius and the distances are in meters. So they give us the temperature at this point, the derivative with respect to x at this point, and then the derivative with respect to y at this point. And they ask us a very typical question for directional derivatives. In which direction does the temperature increase most rapidly? And the answer is in the direction of the gradient of t at minus 1, 2. So your function will increase most rapidly if you move in the direction of the gradient. So you move in the direction 7 minus 3. What is the maximum rate of increase? We said that the maximum rate of increase would be the magnitude of the gradient. See how direct this question is? So this is the square root of 49 plus 9, so the square root of 58. Now this is degree Celsius per meter, right? So the temperature change per meter, not per second, because when you move, the temperature increases. So the temperature per meter. And eventually they can add a chain rule component to this problem. We're going to cover that in the next question. But let's first, I'm going to pause here for a second. Everything's okay. It's different a recording than a live session. In a live session, I would pause and I would say, do you have questions and whatnot? Here, if you have questions, you email me. And if you want to read it again, then you pause and go back. So I can move a little bit faster in a recording. So this is from 2018. Again, directional derivative question. So suppose you are hiking in a mountainous region for which you have a map. Let z be this function. So this is the x and y are the coordinates on the map, and z is the elevation. You are standing at position minus 1, 2. Then what is the slope? The slope meaning what's the directional derivative at this point? right? See, this is not the slope that we've done before, z prime over square root of x prime plus y prime. It's the same, it's just here we have the function, and so we can use directional derivative. I'm not sure how you would use it if in the other function, because you don't have a curve here, right? See, this is a function that's doing a slope. So this is a surface, and you're finding the slope of the surface. So the rate of change of elevation when you move in this direction. So the gradient of z is equal to, in terms of x, that's 3x squared y minus 1 over y. In terms of y, this is x cubed plus x over y squared. Now at the point minus 2, 1, the gradient of z, the gradient of elevation would be 3 times 4, 12, minus 1, 11, minus 8, minus 2 is minus 10. So the directional derivative of z in the direction u at the point minus 2, 1 is equal to the gradient 11 minus 10 dot the vector direction minus 1 minus 2 all over the magnitude of the vector minus 1 minus 2. So this is minus 11 plus 20 over root 5. So this is 9 over root 5. Right? Now, chain rule. This is an example of chain rule. I guess I will explain chain rule first, and then I will do this example, and I don't think there's more. So I'll do this example and another example involving chain rule. So this is the directional derivative. So that means, by the way, since this is positive, that means if you move in this direction, the function is increasing. What's the rate of change? All you have to do is take the well, this is the rate of change, 9 over root 5. Let's say, for example, you increase meters per meters. Like it's you go up a certain meters when you move a certain meter. So when you move 1 meter in this the direction, you go up 9 over root 5 meters in elevation. So now to another topic. So this is how we work with the chain rule. Let's say that we have a function f that depends on, let's say, x and y, or let's make it x, y, and z. And then let's say that x is a function of t, y is a function of t, and z is a function of t. So this is, of course, an example. We could have different scenarios. One can say, what is the rates of change of f with respect to t? Because eventually f would be a function of t, because f is a function of x, then x is a function of t, s is a function of y, and y is a function of t, and so on. So what we do is we follow every path that takes us from f to t. So this is the derivative of f with respect to x times the derivative of x with respect to t. Notice we say d when it's one variable and del when it's multiple variables. So del f del y times dy dt, and then del f del z dz dt. And of course we would be given x, y, and z and so on. Of course it's rare. I haven't seen them ask a scenario where well, like this in APSC 172, but it could be the first time they ask now. So if f is a function of y and z, but then x is a function of r theta and y is a function of r theta. Let's say we're talking polar now. So and let's say that f is whatever, let's say x squared plus 2xy. And then let's do polar. X is equal to r cos theta, y is equal to r sine theta. Then we could ask, what is the derivative of f with respect to theta? Let's say at the point where r theta is equal to 1 pi. For example, of course, I'm just making up these numbers. So this would be the question. And how do we find the derivative of f with respect to theta, the partial? We follow every path that takes us from f to theta. So from f to theta, from f to theta. So this would be del f del theta is equal to the derivative of f with respect to x times the derivative of x with respect to theta, derivative of f with respect to y times the derivative of y with respect to theta. So del f del x is 2x plus 2y. X with respect to theta is minus r sine theta. Derivative of f with respect to y is 2x times derivative of y with respect to theta is r cos theta. Now when r theta is equal to 1 pi, that means xy is equal to, so when I replace 1 pi in here, I'm going to get minus 1, 0. And those are the values that I replace here. So del f del theta is equal to, let's be more clear, del f del theta at the point when r theta is equal to 1 pi is equal to x is minus 1, y is 0, r is 1, sine of theta is 0, sine of pi, which is 0. 2 times x is 1, r is 1, cos of pi is minus 1, so the final answer is minus 2. So that's one other way that they could ask chain rule. Of course, there was the example that we were talking about earlier, which is this one. So we are told that the temperature at any point xy at time t is given to us by this. And an ant is moving, and the path of the ant is this. At time t equals to 3, at what rate is it experiencing the temperature change? So what is the rate of change of the temperature with respect to time? We can say dt, right? Because t is a function of x, of y, and of z, and of t, sorry. Now x is equal to 2t. X is a function of t, y is a function of t. So eventually the temperature is just a function of t. This is a little bit messy, because I mean you can say t is a function of t if you want, right? I mean t equals to 1t. It's a little bit artificial. So dt is the partial with respect to t, partial x, then dx dt, then partial t, partial y, dy dt, then the artificial one, partial t dt dt. Of course, dt dt is 1, right? Because t is equal to t. So del t del x, that would be y plus t. Dx dt is 2. Partial t partial y is x. Dy dt is 2t. Partial t is x. And then dt dt is 1. Now we're saying at time t equals to 3. So if t equals to 3, that means x is 6 and y is 9. So let's replace all of that here. dt dt at the time where t equals to 3 is equal to y is 9, t is 3, x is 6, 2t is another 6, x is 6. So this is 12, 24 plus 36 is 60, 66. And what's the unit? This is degree per, let's say, second, right? Because this is the rate of change of temperature with respect to time, for example. Now, some of you might be thinking, wait, could I have not replaced this and this here and then found the derivative? You could. In this case, in this particular case, you have everything. So you can say t as just a function of t, x is equal to 2t, y is equal to t squared, t is t, and x is 2t. So you discover that this is 2t cubed plus 2t squared. So dt is equal to 6t squared plus 4t. Now at the time where t equals to 3, dt is equal to 6 times 9 plus 4 times 3, which is 54 plus 12, and what do you know, that's 66. So you had that option here, but to be fair, it's not always that we get to do this. It's not always that we have all the given information. Sometimes we don't have the full picture to plug it back in. It's best if we remember how to do the tree, the chain rule tree, and then work out the chain rule in its general form. Right? So that's how chain rule functions. The notion of tangent planes comes up often on tests. So we did cover this on the midterm session, but we're going to cover it again here. So we said that there are two cases. So the first case, if the surface is given to us by z is equal to fxy, and you wanted to find the equation of the tangent plane at, let's say, the point A, B, and f of AB, and then x, y, and then z is f of xy, then we can memorize the formula Lxy, which is the formula for linearization, or basically z is equal to. So when you write it as the equation of the tangent plane, you use z. When you write it as the linearization, so this is the linearization or linear approximation. So they both have the same formula. Tangent plane and the linearization, they both are fz is equal to f of AB plus f sub x at AB times x minus a plus f sub y at AB times y minus b. Again, if we say z equals, then this is the equation of the tangent plane. If we say Lxy equals, then this is the linearization. Now, the more general way to find the equation of the tangent plane is when we have a level surface. So when we have a level surface, let's say f of x, y, z is equal to k. We mentioned this earlier about the gradient. So let's say you want to find the tangent plane at the point A, B, C. You know that the gradient of f at the point A, B, C, that is perpendicular to the surface. It's perpendicular to the level surface at the point A, B, C. Therefore, the gradient vector, we're going to use it as the normal to the tangent plane. So let's say the normal, I'm going to write the gradient as f sub x at ABC, of course, f sub y at ABC, and f sub z at ABC. Again, all of those are at the point ABC, that's a given. So how do we write the equation of a tangent plane where this is the normal vector, this is a normal vector, I should say, and this is the point? So we write it as f sub x, x minus a, plus f sub y times y minus b, plus f sub z, z minus c is equal to 0. And that's how we write the equation of a plane with this as a normal and this as a point. So ABC is the point. Of course, as I mentioned in the midterm session, this case is the more important case. This is the more general case, because even if you're given z is equal to fxy, you can transform it into z minus fxy equals to 0, and that becomes your level surface, fxyz equals to 0, and then you can just use this technique. Again, there's nothing wrong with using this. It's totally valid, and there's nothing wrong with using this. I'm saying the level surface technique is the one that works all the time. Right? So let's practice. Here's what they asked in 2020 for tangent planes. So let f be a function of x, y, z. We have a level surface fxyz is equal to 2. See, we've seen this problem before. We used parts of this problem before. The level surface defines a function z is equal to fxy. Again, we used part I before. They gave us f sub x is 3, they gave us f sub y is 1, and they gave us f sub z is minus 2. And they've asked us to find the equation of the tangent plane. Well, the equation of the tangent plane to the surface z is equal to fxy. We need to find z sub, right? So z is equal to f at AB, and f at AB is minus 1, right? Because this is A, this is B, and this is f at AB. Now we have f sub x. We found those in a previous problem. F sub x, f sub y, f sub z. So x minus A plus f sub y at AB times y minus b. Remember, we found this in a previous problem. This is minus f sub x over f sub z, so that would be 3/2. And this one is minus f sub y over f sub z, which is 1/2. And f of AB, we said that this is equal to minus 1. Right, so this is z is equal to f of AB is minus 1 plus 3/2 x minus 1 plus 1/2 y, and that's the equation of the plane. Now, you're saying, okay, wait, could I have not used the level surface? And of course I could have. See, in case that you remember, we got those values using the implicit functions theorem. We did this earlier. But in case we didn't know the implicit function theorem, or in case we forgot it, or in case it wasn't covered, we can use the level surface. So we can say that the normal to the plane is going to be the gradient, which is 3, 1, minus 2. The point that we're doing the tangent plane is 1, 0, minus 1. So the equation of the tangent plane is 3 x minus 1 plus 1 y minus 0 plus actually minus 2 z plus 1 equals to 0. I want to show you that this will give you exactly this, that this and this are exactly the same. Look, you have 3x minus 1 plus 1 times y is equal to, minus 2z minus 2 equals to 0. Move the z over to the other side, so 2z is equal to 3 times x minus 1 plus 1y minus 2. And then divide, this is minus 1. I was looking for the mistake. That's minus 1. So z is equal to, divide everything by 2, 3/2 x minus 1 plus 1/2 y minus 1. And you see, we get the exact same answer. So I personally prefer this method. I just did the first method just to say that we did find f sub x and f sub y earlier, and I wanted to show you that both methods work. But my preference is always, if I can, the level surface. It's a very straightforward method. And again, if you haven't done the implicit function theorem, then your only solution is to use the level surface method. Let's do some other problems. So here we go. We have a level surface here. Tx, y, z is equal to 2. So here we have no choice. We don't have an fxy. We don't have z equals to fxy. Technically we can. If you set this equals to 2, you can solve for z, but let's not. Y actually do more work than we need to. So the normal n is going to be the gradient of t at the point 2, 1, 1. So the gradient is 2x, 3y squared and minus 3. At the point 2, 1, 1, we're going to choose n to be 2 times 2 is 4, 3 times 1 minus 3, and the point is 2, 1, 1. Again, simple question. This was asked on 2019, the final of 2019. So 4 times x minus 2 plus 3 times y minus 1 minus 3 times z minus 1 equals to 0, and you can expand and simplify. As we've seen on the midterm sessions, see, this one is similar. I'm going to leave that up to you. This one is exactly the same. So we're going to we write it as z minus x e to the xy is equal to 0. So that becomes my level surface fxyz equals to 0. Well, I said I would leave it, but I'm doing it now, so it takes a minute. Let's finish it. So the gradient of f, which is going to be a normal vector, the derivative with respect to x is the derivative of the first times the second plus the first times the derivative of the second. The derivative with respect to y is minus x squared e to the xy. The derivative with respect to z is 1. Now at the point 2, 0, 2, so at the point 2, 0, 2, the gradient of f is equal to, when y is 0, that's minus 1. When y is 0, that's minus 4 and 1. And the point is 2, 0, 2. So minus 1x minus 2 minus 4y minus 0 plus 1z minus 2 equals to 0. So another simple equation of the tangent plane. I wanted to maybe do one that is a little bit one that we would find an equation of the tangent plane containing a point or something. So I'm going to look for that problem, and then I will create it. I will continue the videos once I've posted it. So for one more example on finding the equations of the tangent plane with a little bit of twist. So we want to find the equation of the tangent plane to this surface that contains all of the x-axis. We did something similar in the midterm session if you were there. We said there it contained a different line. Now we're just saying it contains the x-axis. So let's create our function f(x,y,z). So I'm moving, for once I'm moving the z over, right? So 2y squared minus z plus 16 equals to 0. Whatever, you can just, as long as you move everything to one side and make it equal to a constant. So this is my function f(x,y,z). This. So I'm setting the gradient of f is the function 2x plus 2y, 2x plus 4y, and then minus 1. Now at the point right here, so at the point right here, we're gonna get the gradient of f is equal to 2a plus 2b, 2a plus 4b minus 1. That's a normal to the tangent plane. And then we have this point right here. So the equation of the tangent plane is 2a plus 2b x minus a plus 2a plus 4b y minus b minus 1 z minus all of this equals to 0. Now what's the key point here? We want this plane to contain the x-axis. What is the x-axis? The x-axis is x equals to t, y equals to 0, and z is equal to 0. So we want that if we plug in the equations of the z-axis into the equation of the tangent plane, we want to get an equation that's equal to 0 for all t. So regardless of the t value. So when I replace this in there, this is 2a plus b times t minus a plus, I'm leaving this 2a plus 4b because I'm expanding it, times minus b minus 1 times minus a squared minus 2ab minus 2b squared minus 16 equal to 0. And we wish this equation to be true for all t. Fantastic. So I have 2a plus b times t minus, now this multiplied by a, I'm going to expand everything else. So that would be minus 2a squared minus 2ab minus 2ab minus 4b squared plus a squared plus 2ab plus 2b squared plus 16 equals to 0. Now let's do some tidying up. 2 times a plus bt minus 2a squared plus a squared is minus a squared. Minus 2ab plus 2ab is gone, then I have minus 2ab. Minus 4b squared plus 2b squared is minus 2b squared plus 16 equals to 0. Now, as we said in the midterm session, we say again, we want this to be equal to 0 for all t. That means this has to be 0 and this has to be 0. That way we ensure that the equation is 0 regardless of what t is. So this equals to 0 gives us a equals to minus b. So I replace that here. There I get minus a squared plus 2a squared minus 2a squared plus 16 equals to 0. That gives us a squared is equal to 16. So a is equal to 4 or equals to minus 4. So here you get b equals to minus 4 or b equals to 4 here. So we got 2 points. They just wanted a point, find a point, but we found 2 points, so whatever. So this one is point AB, and then you replace them. Don't forget that the full point is this. So to get the point, you plug this in here, you get 1 point, and you plug this here and you get a different point. And those are the points where the tangent plane would contain the entire x-axis. Just wanted to do a little bit of a different problem for tangent planes before moving on to other topics. Let's now discuss linearization, which is a way to approximate a function fxy with a function lxy that is much simpler. In fact, it's a linear function. Now, when we have two variables, we know that we've seen this formula when we talked about tangent planes. Lxy, which is the equation of linearization, which is basically the equation of the tangent plane when we are in R3, when there's a function fxy. So near the point AB, Lxy is f at AB plus f sub x at AB times x minus a plus f sub y at AB times y minus b. Now what I want to stress here is that yes, if you change this to a z, you get the equation of the tangent plane, but linearization is not only limited to two variables. You can have a L, X, Y, Z. So you can have a function X, Y, Z, and you approximate it by a linearization L, X, Y, Z near, let's say, the point A, B, C. You can have any number of variables, and the extension to an extra dimension works exactly the same way. So this times x minus a, the derivative with respect to y at ABC times y minus b, plus the derivative with respect to z at the point ABC times z minus c. So for any level, for any number of variables, we can find an L that approximates f. Here's what they asked in 2020. So we have a temperature, Txy, and they gave us t at this point, and they gave us the gradient tx and ty at that point, and they asked us to write a linearization. So they basically gave us everything. We just need to plug it in. Lxy is equal to t of minus 1, 2 plus t sub x at minus 1, 2 x plus 1 plus t sub y at minus 1, 2 times y minus 2. And we just plug in the values. So this would be 35 plus 7x plus 1 minus 3y minus 2. Naturally, now they ask you to use it to approximate a certain temperature. So T of minus 0.9, 2.05 is approximately the same thing as L of minus 0.9, 2.05. And plugging those values in here, this is a very easy function to work with. This is 35 plus excuse me, 7 minus 0.9 plus 1, 2.05 minus 2. So this is 35, this is plus 0.7, and this is 0.05, so minus 0.15. So this is 35.55. Right, this is not a particularly complex topic. Here's another example that they asked in 2019. So I don't know, maybe pause and try this on your own. I know that a pre-recorded session and on-demand session moves faster than a live session because I'm not stopping for questions, I'm not giving you time to solve it, but it's also, you know, very easy. Just click pause, solve it, and then unpause, and then you'll get me solving it. So let's see. The linearization Lxy is equal to f of 1, 2, f sub x, x minus 1, f sub y, y minus 2. So f of 0.9, 2.2 is approximately equal to L of 0.9, 2.2, which is 4 minus 1, 0.9 minus 1, plus 3, 2.2 minus 2. So 4 plus 0.1 plus 0.6, so 4.7. And that's how linearization functions, ladies and gentlemen. Our next topic now is contour maps, which is a topic that is not particularly the favorite of some students, but I decided to choose problems other than the ones I did in the midterm session, again, so you can get maximum practice. I also did some questions that are not like super typical, so not the ones that like draw the gradient or something. Those we've done in the midterm, and I chose the problems that were on past finals. So this is from the final of 2020. So below is a contour map, so a bunch of contour lines, a bunch of level curves, and they are of the circular paraboloid. So this is a paraboloid that goes like this. So we're taking contour maps of it for every level of z. Obviously they're all circles. The contour maps are at intervals of z is equal to 1, so each one is a z equal to 1. We begin at the point 4, 0, 0. So we begin here. This is the point 4, 0. Of course, we don't have elevation. Elevation isn't drawn here. And ascend the hill in such a way, so you're going around the hill. Again, there's a hill like this, and you're going to the top of the hill, so you don't see it right here. You're just going like this, in such a way that the projection of my path onto the xy plane is the semicircle. So this is the projection of my path of radius 2, 0, y bigger than or equal to 0. Suppose that this projected point moves at a constant speed, and the entire journey takes 4 seconds. So I'm starting here and I'm going all the way here, and that should take me 4 seconds. So find an equation for my elevation z against time and draw it on the graph. So let me try and find, see if I can find what x and y are in terms of t, then I can plug them here, and that would give me my elevation z against time, z as a function of t. So since my path x and y, so my goal is to find what is x, I'm just going to look at this, what is x and what is y equal to in terms of t. Okay, look, it's clear that we're going to use cosines and sines because the path that we go to, the path is a circle. Now, it's a circle that starts here. It doesn't start at 0, 0. So, and it's a circle of radius 2. So, yes, you want to say 2 cosine something t and 2 sine something t, because that gives us the radius of 2, right? But then cosine, first of all, when I start at t equals to 0, so we're clear that this is theta equals to 0, right? When theta equals to 0, I'm right here. Or when t equals to 0, I'm here. Now, when t is equal to this, right? So, like when I did half a turn, so technically, when t equals to pi, I should get here. Like I did like 180, right? I turned 180. So, when t equals to pi, I'm here. So, what should be, first of all, something is missing here. Because when I put t equals to 0 here, that will give me 2 and then 0. 2, 0 is here. I don't want 2, 0, I want 4, 0. So I need to add 2 here. So now when t equals to 0, I get 4 and 0. So when I'm here, now when t equals to pi, excuse me, I'm supposed to get 0, 0. So I'm supposed to get 0, 0 when I put t equals to pi. There's no problem here, but here, how do I make this go to 0? How do I make this go to minus 2? Because this would be minus 2 plus 2 would give me 0. How about I put pi over 4 here? Let me think about this for a second. So 2 cosine pi over, excuse me, pi over 4, t over 4. 1 over 4t, and this would be 1 over 4t plus 2. Let me think for a second. And then we're gonna, it takes 4 seconds. So when t is equal to 4, I'm sorry, this should be pi and this should be pi, sorry. Because we're gonna take, this is t equals to, I said pi, that's a mistake. This is t equals to 4 seconds. This is time, this is not theta. So let me start again, sorry about that. This is, I'm here when t equals to 0, and I'm here when t equals to 4, time, not theta. Yes, theta, I did the whole pi, but that's not time. Theta is not time. So when I put t equals to 0 into this, when I put t equals to 0, I will get x equals to 4, y equals to 0, which works perfectly. When I put t equals to 4, I'm going to get x is equal to 0 and y equals to 0, which is perfectly. So I finished my whole path in 4 seconds. Right? So I finished my whole path in 4 seconds. Right? So it's like saying theta starts at 0 and it goes to pi in 4 seconds. So theta goes from, I can't write anymore, 0 to pi in 4 seconds. So that's what I want here. So this is why I decided to make theta, the inside here, pi over 4t. Again, aside from this argument, just use the arguments of where are you at t equals to 0 and where are you at t equals to 4. So at t equals to 0, you are at the point 4, 0, which works beautifully here. And when you're at t equals to 4, you needed this to become minus 1. So this is why when you put t equals to 4, you get cosine of pi, and cosine of pi is minus 1, and that works beautifully. Now, as I said, you want the elevation z against time, so that's very simple now. Z is equal to 16 minus x squared, so that's 4 cosine squared pi over 4, no, cosine, sorry, this is 2 cosine pi over 4t plus 2 all squared plus 2 sine pi over 4t all squared. So here we could just do 4 sine squared. So let me simplify this. This is z is equal to 16 minus, this is 4 cos squared, right? So this is going to be 4 cos squared plus 8 cos plus 4. And then 4 cos squared plus 4 sine squared, that's 4. So this would be 4 plus 8 cosine pi over 4t plus another 4. 16 minus 8 is 8 minus 8 cosine pi over 4t. Right? And draw its graph on the set of coordinate axis below. Oh, well, it's drawn, 8 minus cosine. So basically draw cosine, then minus it, then add 8. So this is how the graph looks like. So, right, so cosine pi over 4t, if we do this really quickly. So when t equals to 0, this will be cosine of 0, so it will be 0. I'm going to use actually a graph that looks like the one that they gave us. So when t equals to 0, z is equal to 0, my elevation is 0. I want to say obviously, but I don't know if it's very obviously. When t equals to 4, I'm at 16. Because when t equals to 4, I've reached the top of my hill. And this is a, let's say for t equals to 2, that would be pi over 2, cosine pi over 2, 0. So I've reached 8. And this is a cosine function, right? So like this, and then like this, and then like this, and then like this, so on. So this is a cosine function, so you can expect it to be something like this. Right? At what point is my vertical speed maximum? So I want my vertical speed, so I want z prime to be maximum. Z prime is 8 times pi over 4 sine pi over 4t, and we want this to be maximum, so that means pi over 4t must be pi over 2, because that's the maximum that we can get out of sine when sine of pi over 2 is 1, so that's the maximum sine. Therefore t is equal to 2 seconds, or 2 minutes. Is it seconds? Yeah, 2 seconds. So here is my largest speed, and it kind of makes sense also if you look at the graph. The speed is the derivative, so the tangent line keeps increasing until here. This is the largest tangent line, and then the tangent line starts increasing after. So this is where we have the maximum slope of the tangent line. So the maximum z prime, which is the maximum vertical speed. Right? So Now they changed the question a little bit. So now we're climbing the same hill with the same semicircular path. But now we make the x coordinate a decrease at a constant rate. So x decreases at a constant rate. So you're going to start at the point 4, 0, and you're going to end up at the point 0, 0. So x will decrease from 4 to 0 at a constant rate. So x will be 4 minus t. Right? It's a constant rate. So x will decrease at the rate minus 1. Again, x prime is minus 1. So the rate at which x increases is minus 1, which is a constant. Now, we need to figure out what y is, and then we plug it back into z and we do the whole thing, right? So we need to figure out what y is. Like here, we figured out what x and y are. We plug them into the elevation, and that gives us z. So what is y? Well, we know that this circle, the equation of this circle, is x minus 2 all squared plus y squared is equal to 4, because it is centered at 2, 0 and of radius 2. So plug in 4 minus t here, get y squared. So y squared is equal to 4 minus t minus 2 all squared, which is equal to 4 minus 2 minus t all squared. So this is 4 minus 4 plus 4t minus t squared. So this is 4t minus t squared. Now I don't technically need to get y because my z is in terms of y squared. Whoa, no. What did I do? Something happened. Here we are. So back to this. So this is my z, and my z is in terms of y squared, so I don't really need to resolve for y. So I get z, my elevation, is 16 minus x squared, that's 4 minus t all squared, plus y squared, so plus 4t minus t squared. And see what happens. This is 16 minus, this is 16 minus 8t plus t squared plus 4t minus t squared. So t squared minus t squared is gone. So this would be 16 minus 16, and then minus 8t plus 4t is minus 4t, with a minus is 4t, and therefore z would be equal to 4t. How simple is that? They want us to draw it. You can see that 4t looks like this. At what point is my vertical speed maximum? Well, the vertical speed is constant, right? So the vertical speed is is z prime equal to 4 at all times. So your vertical speed, like your x speed, is constant, is equal to 4 at all times. So that's one type of problems that deals with contour maps. Again, it was asked in 2020. It's an interesting question. It deals with equations of path that are circles. It deals with speeds and constant speeds. I hope that you find that useful. Now we're going to solve another one. Continuing with contour maps, let's look at what they asked in 2019. So the temperature at any point xy is txy. The contour plot for t is given. Contour lines are spaced at the interval of t equals to 1, so that's very, very useful. Also, tx0 is increasing for x in the interval minus 1 to 1. So from here to here, tx0, so as x increasing, the temperature is increasing. So I don't know what these values, where each one of those values are, but we know between minus 1 and 1, it's increasing like this. So the direction of increasing is that way. So an ant is at the origin, so our ant is right here. I don't know, blue is better maybe. So here's the ant. It's moving with velocity, right? So the velocity is 0.4, 0.3. So that means dx dt is 0.4 or x prime, and dy dt is 0.3. At what rate is it experiencing the temperature change? So we want to find dt dt. Remember chain rule? So t is a function of x and y, and then x is a function of t, y is a function of t. So that means, how do I find dt dt? It is the derivative del t del x dx dt plus del t del y dy dt. Excellent. Now dy dt and dx dt, I have them. But at 0, 0, again we're at 0, 0, what is the gradient? So what is this and what's this at 0, 0? Basically what we're asking is, what is the gradient of t at the point 0, 0? Because that's delta x, delta y. So you want to draw the gradient here, and here's where we use the knowledge we know about the gradient. The gradient is perpendicular to the level curve in the direction of increasing t, so that's my gradient. Right? Now, the gradient looks like this, right? So now if I go 1 unit along this direction, if I go 1 unit, my t jumps 1, 2. So the rate of change is 2. That means the magnitude of the gradient in this region is 2. Again, approximately it's like if I go 1 unit, it's 2 point something. So the magnitude of the gradient is 2 point something. Approximately this. So the gradient of t is approximately the vector 2 and then 0, right? There is no change in y. The gradient is perpendicular to this curve. It's entirely horizontal, so that would be del t del x, and that would be del t del y at the point 0, 0. Right? It's perfectly horizontal, so it has no y component, and those are the values that we use here. So we're approximating this to be 2, 0. Again, it's 2 point a little bit more. I don't know how much that a little bit more is, right? See, like there's just a little bit here, but I'm comfortable just saying like 2. Actually, it's a little bit, yeah. So let's just say 2. 2 is a fair approximation. So that means the ant is experiencing the rate of change. So let me redraw delta t, gradient of t. So the ant is experiencing temperature change at 2 times 0.4 plus 0 times 0.3, so 0.8 degrees per second, whatever, or per meter or whatever, they don't specify the units. So that's how we do that question, and that question was asked in 2019. Now let's look at another question that they asked us in 2019 about contour maps. So the temperature again is Txy. The contour plot for T is given here. Contour lines are spaced at intervals of 0.5. So the jump from one contour map to the other is 0.5. The point of maximum temperature is 0, 1. So maximum temperature is here. It's nice. You could see it like in the middle of this. It's in the middle, 0, 1. And the temperature decreases from there. So temperatures decrease from this point on. So as you go that way, temperatures are decreasing any way you go away from that circle. Great. On the diagram, draw an arrow representing the gradient t at the point 1, 2. So how does the gradient look at this point? First of all, we need it to be perpendicular to this level curve. So let me draw a direction perpendicular to this level curve. I'd like to think this is perpendicular to the level curve. Right, let me draw the level curve. Right, so it seems perpendicular. Now, in which direction are we going to go? We're going to go with the direction increasing. So we're going to go this way. So the gradient will be this way. Now, how long are we going to go this way? Right? Put the tail of your arrow at the point 1, 2. Take care of both the length and the direction. The direction is perpendicular to this level curve, so we're good. Now, in terms of length, okay. What's the magnitude of the gradient? Remember, we talked about this when we did directional derivative. The magnitude of the gradient is the rate of change of the function. It's the maximum rate of change of the function when you move in the direction of the gradient. So when you move in this direction, right, when you move in this direction, the magnitude of the gradient is the rate of change. So basically, we pick 1 unit, and then we take that 1 unit and put it here, approximately. So how many curves are we crossing? It was approximately here. So we're going 1, 2, 3, 4, I don't know, 4 and a bit. So 4.5 if you want. I don't know, like, because here we're gonna cross this, but then we're on our way to cross it back. So I would say if this is 1 unit, approximately 4.5, approximately. But then every jump is 0.5. So the rate of change in this is 4.5 level curves, 0.5 every level curve. That's 2.25. So I would say the magnitude, this would be the magnitude of our gradient of t. So 2.5 units. So if this is 1 unit, of course we could use a ruler. So let me see if I can find the ruler. I can't find the ruler. Hold on. There's a ruler here. Here we go. So what's 1 unit at this level? It's 5 centimeters. Wow, there's a ruler here. I didn't know, but I don't like it. So there's 5 centimeters approximately. So I'm going to use 10 centimeters, 0.25. So here we go. So approximately this is the gradient. So my gradient is this. And again, the magnitude of the gradient is about 2.25. Right, so remember, the magnitude of the gradient is how is the rate of change of the function in that direction. So, and the rate of change in that direction, you pick up 1 unit, you see how many level curves you cross, you multiply by the jump of from one level curve to the other. That gives you the the rate of change in that direction, and that's how you draw your arrow. Fair enough? Let's do other problems. Let's do one from 2018, though after a short break. So this is the contour maps problem from 2018. Again, I tried to get you new problems that are not the same ideas as the ones before to get a maximum level of practice. So below is a contour diagram for the inverted parabolic trough, and z is equal to this, right? For x is bigger than or equal to 0, the contour lines are spaced at z is equal to 1/2, so you have it here. A bug begins at the origin and walks up through the trough, always ascending at slope 1. This is very important. Always ascending at slope 1. So the bug will always move up at slope 1. So use the information provided by the contour diagram to make a sketch of the projection of the bug's path on the xy plane. Your path does not have to be exact, it has to be reasonable. Note that the bug won't be able to get all the way up. At some point the hill will not have a slope equal to 1, so you have to stop. So let me explain to you. What's the maximum rate of change on that hill? If you're standing at any point, what's the maximum rate of change? The maximum rate of change or the maximum slope, that is the magnitude of the gradient of f at any point. So the bug wants to always move at slope 1. But what if this is less than 1? What if you're standing at a point where the slope is nowhere bigger than 1? So the slope, let's say, is always 0.5, or the slope is always less than 1. Then the bug cannot move any further with slope 1, so the bug has to stop. So this is what they mean, that at some point the bug cannot continue because the bug will not find the slope equal to 1. Okay, what is the gradient of f in this case? That would be 0 and then 4 minus 2y. So the magnitude of the gradient of f is the absolute value of 4 minus 2y. I take absolute value because I'm not really sure if it's positive or negative. Now, where is 4 minus 2y less than or equal to 1? So you can keep moving as long as the 4 minus 2y, sorry, it is between minus 1 and 1. As long as this is less than or equal to 1, you could always move at slope 1. They didn't tell us that it has to go up. It could go down or go up. So that would mean 2y minus 4 is between minus 1 and 1. So 2y is between 5 and 3. And then y is between 3 halves and 5 thirds. So did I do this right? So minus 2y multiplied by negative. Right, so when we get this, the bug stops. So when we have, let's say, less than 1, right? So when we get a maximum slope, I remind you that the magnitude of the gradient is the maximum slope. So when the maximum slope is less than, we can keep the less than or equal, doesn't matter. So when the maximum slope is less than or equal to 1, that means the bug stops. So the bug will stop as soon as we reach 3 halves. So this is why they say 3.5. So as soon as y reaches 3 over 2, which is 1.5, so this is 1.5, the bug cannot go beyond y equals to 1.5. Okay, how do I draw the path? How did we come up with this path? The bug has to move with slope 1. So every time you move 1 unit on the x, you should move 1 unit on the y. So 1 unit on the y, that means 2 contour maps. Right? So for every 1 unit on the x, approximately, you should move 2. So to move 1, you should move 2 contour maps. So at 1, you're supposed to be here. Now you move 1 more unit with x, you're supposed to jump 2, so you're approximately here. You move 3 units, 1, 2, you're approximately here. And then you're at y equals to 1.5, you stop. So create a reasonable path joining these points. They came up with this. Our path would be just a little bit like this, but basically the same idea. Right, so when you move 1 unit in x, you need to cross 2 level curves, because the slope you want to go up is the bug wants to move at slope 1, right? So the bug wants to move at slope 1, so 2 level curves every time. So with every 1 unit of x, you're going to move to, technically, with every 1 unit of x and y, right? Because with every 1 unit in any direction, not just x. But approximately, if you move 1 unit with x, you're going to get 1 unit of y, and that's going to get us this path. Now, this one is a little bit more tricky. I actually had to read it a few times. So focus on the path that you had to sketch in A. Calculate the theoretical value dy over dx. So find what dy dx is. What's the rate of change of y with respect to x? Note that this is different in the sense of the slope than in A. We took z to be. Here we're just looking at the rate of change of y with respect to x. So how is y changing with respect to x? So let's see. Let's say that the bug, so we know that the gradient of f is equal to 0, 4 minus 2y. Let's say that the bug moves in the direction 1. I'll tell you why I choose 1k. So let's say that the bug moves in the direction 1k, right? So what would be dy dx? Basically, dy dx would be the rate of change of y with respect to x, and that would be k. Think about it. We're saying the bug moves in the direction 1k, which means for every 1 unit of x, there will be k units of y, and then the rate of change of y with respect to x would just be k. Okay, but then how am I going to find k? Well, the only other thing I know is that the bug moves at slope 1. So when I take the gradient, the dot 1k divided by the magnitude of 1k, so when I take the directional derivative, I'm supposed to get 1. This is the only thing I know. So the only thing I know is that the directional derivative is 1. So that means 0 times 1 is 0. So 4 minus 2y times k. So 4 minus 2yk divided by the square root of 1 plus k squared is equal to 1. So 4 minus 2y k is equal to the square root of 1 plus k squared. I'm looking for k, so if I square both sides, 4 minus 2y squared k squared is 1 plus k squared. So that means 4 minus 2y squared minus 1 k squared is equal to 1. So k squared is equal to 1 over this, 4 minus 2y squared minus 1, and therefore k is equal to 1 over the square root of all that. That's what I came up with. I checked the solutions provided to the students that year, and it's the same, basically the same idea. So again, we want to find dy dx. So what's the slope? Again, dy dx is the slope of the path, right? So if the bug is moving in the direction 1k, so here's the bug is moving in the direction 1k, right? That means the slope is going to be equal to k, and then we found it in terms of y, which makes sense because at every point, like, it's going to be moving in a different direction. So here it's moving in this direction, here it's moving in this direction, here it's moving in this direction. So at every point it's moving in a different direction. So the direction will depend on x on y. Here we see that it depends on y. So if it's moving in this direction, dy dx would be basically k. The only other thing we know is that the directional derivative is 1. So we write the equation of the directional derivative, we solve for k, and that's the answer that they want. So Congratulations, that's contour maps. Another topic that I want to look at in this part is the partial derivatives and implicit differentiation. It's a part that doesn't usually get asked directly on tests. It's asked indirectly through other questions, so I'm not spending a lot of time on it. I'm just going to cover it with you and to make sure you understand the basics, and then we'll move on to other topics. So how do we find the partial derivative of, let's see here, what's the derivative of f with respect to x? So the partial derivative of f with respect to x, we consider y to be a constant, and then we derive, you know this. So this would be e to the x plus, or y e to the x, I'm sorry, because y is a constant, and then the derivative here is x to the power a constant, so that would be y x y to the minus 1. For example, what would be the derivative of f with respect to y? That would be, in this case, e to the x plus, here it's constant to the power y, so it's constant to the power y times ln of the base times ln of x. Now, we know that when we do functions of multiple variables, there are mixed derivatives and double derivatives and all that. So what would, let's say, be fxx is the derivative of f with respect to x twice. So here we would get y. Let me write it down for you. This is the derivative with respect to x of the derivative with respect to x. And that would be, we're deriving this with respect to x. So y e to the x. Now y is a constant, and the derivative of this is y times y minus 1 x to the y minus 2. For example, what would be the derivative fyy? So the derivative with respect to y is of f of y here. That would be x to the y times ln x, but then there's times that ln x that's already there, so times ln x squared. There's what we call mixed derivatives, which is fxy. You know by Clairaut's theorem that for all the functions that we encounter in 172, it doesn't really matter. The order of derivative won't really affect your answer. So fxy is the same thing as fyx. So you can derive first with respect to x, then with respect to y, or with respect to y, then with respect to x. So I'm going to take this and I'm going to derive it with respect to x. That would be e to the x plus, now here we have a product rule, derivative of the first times the second plus the first times the derivative of the second. And if you took the derivative of y of x and then you derived it with respect to y, you would get the exact same answer. So that's partial derivatives, that's great. I want to talk to you now about implicit differentiation. So here's an example that I quickly made up. We have an equation that defines z as a function of x and y near the point 0, 1, 1. So they tell us that z is a function of x and y. It's given to us by this equation. How do I find del z del x, and how do I find del z del y? We saw this earlier using the implicit function theorem, but I'm going to do it using the regular implicit differentiation way. I won't use the implicit function theorem here. So I basically, take this and then I derive with respect to x. So I take this and I derive it with respect to x. That gives me 2x times e to the z plus x squared times e to the z times del z del x. Don't forget that z is a function of x, so here we have two functions of x and I'm using a product rule. Here minus 4y del z del x plus 16x plus 0 equals to 0. So now I isolate del z del x. That gives me x squared e to the z minus 4y equals minus 16x minus 2x e to the z. And finally, del z del x is equal to minus 16x minus 2x e to the z. divided by x squared e to the z minus 4y. Now we can find it at a certain point or not. Let's now focus on getting del z del y. Same idea. So now I derive with respect to y. So this is x squared e to the z, and then this is del z del y. Here we have a product rule. Derivative of the first times the second plus the first times the derivative of the second. And that's equal to 0 because x is a constant in this context. So I factor out del z del y. We get x squared e to the z minus 4y equals to 4z. So del z del y is equal to 4z over x squared e to the z minus 4y. Right? Now how could they ask us to use this? They, for example, can ask us to use linearization to approximate the value of z at a certain point. Now please note, they give us this point, so this one right here, that's z of 0, 1. So how do I write the linearization for zxy? I'm going to do part B here so we can still see all the values we found. So we know that Lxy is z, of course near the point 0, 1, is z01 plus z sub x at 0, 1 times x minus 0 plus z sub y at 0, 1 times y minus 1. Now we have z sub x and z sub y. So here, if I find this at the point 0, 1, 1, del z del x would be, if x is 0, so that's 0 outside. And if here at 0, 1, 1, z sub y is going to be 4 divided by minus 4, which is minus 1. Therefore, Lxy is equal to 1 plus 0 minus 1 times y minus 1. So if I wanted to find z of 0.1 minus 0.9, that's approximately equal to L of 0.1 minus 0.9, and that would be 1 minus 1 times minus z is 1, so we shouldn't have minus here. It should be close to 1, so it should be 0.9, like it should be close to the point 0, 1, right? So the way I asked it wasn't, so it should be 0.9, so that's 0.9 minus 1, and that would be 1.1. Right, so that's implicit differentiation and a possible way of using it. Let me ask you this question. How would I be able to get this in a different way? How would I be able to get to this in a different way other than implicit differentiation? And the idea is that if you replace this by z, right, remember that this would be the equation of the tangent plane. If you replace the Lxy by z, we said this would be the tangent plane. So we could find the equation of the tangent plane here using the other method of the gradient method, and then isolate for z, and that will give us exactly that look. If I take this, I'm going to just show you that we do get exactly the same answer. So let's call this the function fxyz. So this is the level surface. The gradient of f, now with respect to x, that's 2x e to the z plus 16x. With respect to y, that's minus 4z. With respect to z, it's x squared e to the z minus 4y. At the point 0, 1, 1, the gradient of f is 0 minus 4 minus 4. So of course I could use 0, 1, 1 if I wanted. So I could use the vector 0, 1, 1 as normal to the plane, or I could just use the same vector 0 minus 4 minus 4, right? Because we talked about this. If this is the normal, then this is a normal, then this is a normal, then this is a normal, right? The length of the normal vector doesn't really matter. So use whichever vector you want. The point is 0, 1, 1. So the equation of the tangent plane is 0, x minus 0, plus 1, y minus 1, plus 1, z minus 1 equals to 0. So y minus 1 plus z minus 1 equals to 0. So z is equal to minus y plus 2. Let's look here. What's z equal to? So look here. Lxy is equal to 1 minus y plus 1, which is 2 minus 1. So you get exactly the same answer. So you could have used this as your Lxy. I'm just showing you a different way of doing this. And this problem served three purposes: implicit differentiation, review of tangent planes, and linearization. So we used a lot of topics to review within the same problem. One of the last topics that we covered in the midterm was the finding the critical points of a function fxy and then classifying them as local min, local max, and saddle point. The theory goes as follows. To get the critical points, we solve f sub x equals to 0 and f sub y equals to 0. So we solve those points. Once we have the critical points, to decide whether they're a max, a min, or a saddle point, we do the following. We find fxx, we find fyy, and then we find fxy. Then we form a quantity d for every point, which is fxx times fyy minus fxy all squared. And based on these, we decide whether we have a min, a max, or a saddle point. So if d is less than 0, then automatically we have a saddle point. If d is bigger than 0 and fxx is bigger than 0, then we have a local min. And if d is bigger than 0 and f of xx is less than 0, then we have a local max. You won't have to face the case d equals to 0. It's extreme. I've never actually seen a problem with d equals to 0. So I'll give you the example that was given in 2015, the midterm though. I haven't seen this on a final in a while. So they gave us f of xy is equal to x to the 4 plus 3x squared y minus 2 plus 6y minus 1 squared. They told us to find the critical point and to classify them. So let's go ahead and do that. What is f of x? F sub x, the derivative with respect to x, is 4x cubed plus 6x times y minus 2. And we want this to be equal to 0. What is f sub y? That's going to be 3x squared plus 12 times y minus 1, and we want this to be equal to 0. So now we need to figure out a way to solve this system. So one way to do this is I'm going to isolate for y here, replace it here, and then solve. So that's 3x squared plus 12y minus 12 is equal to 0. So 12y is equal to 12 minus 3x squared. So y is equal to 1 minus x squared over 4. Great, let's replace that in here. We're going to get 4x cubed plus 6x. 1 minus x squared over 4. 1 minus x squared minus 4 minus 2 is equal to 0. So that would give me 4x cubed plus 6. You know what, let's tidy up here. This is minus 1 minus x squared over 4. So 4x cubed minus 6x plus 6x cubed over 4. So 3x cubed over 2 equals to 0. I don't know why I say plus, it's still minus. Right, because it's plus 6x times this and then times this. So that gives me, let's multiply everything by 2. 8x cubed minus 12x minus 3x cubed equals to 0. So 5x cubed minus 12x equals to 0. And that gives us, we can factor out an x. That gives us 5x squared minus 12 equals to 0. So either x is equal to 0 or x squared is 12 over 5 or 2.4. So x is equal to plus or minus the square root of 2.4. So if x is equal to 0, y is equal to 1. If x is equal to the square root of 2.4, or x is equal to minus the square root of 2.4, doesn't matter, because y is equal to 1 minus x squared over 4. So y is equal to 1 minus x squared is 2.4 over 4. So y is equal to 0.4. Fantastic. Now we have to go ahead and find fxx. So let's do them here on the side. Fxx is equal to the derivative with respect to x. That's 12x squared plus 6 times y minus 2. Fyy, I'm taking the derivative of this with respect to y, which is 12. Fxy, I'm taking this and I'm deriving with respect to x, so that gives me 6x. So now we need a very nice table with all of these points. So that's the first critical point, that's the second critical point, that's the third critical point. The first one is 0, 1, root 2.4, 0.4, minus root 2.4, 0.4. So we need fxx, fyy, fxy, and then we need d is equal to fxx fyy minus fxy squared, and then we get the result of what this is. Of course, fxx is 12x squared plus 6 times y minus 2. This is 12, this is 6x. So let's see. Here fxx, if x is equal to 0, y is equal to 1, that's minus 6, that's 12, that's 0, d is negative, so this is a saddle point. Maybe pause for a second, try and fill it on your own and you'll get the exact same result. Here, that's going to be 2.4. We need the calculator. So 12 times 2.4 plus 6 times 0.4 minus 2. That's 19.2. That's 12. And then 6 times x, so 6 times the square root of 2.4. D will be positive in this case, and fxx is positive, so this is a local min. Here again we're going to get 19.2, again 12, now minus 6 root 2.4. Really doesn't matter, we're going to still get positive, this is still a local minimum. So that's how we found the critical points and we classified them. All the examples are the same, and we've done a couple of problems in the midterm sections. And one of the last topics, if not the last topic of the midterms, is differentials. This is not a popular topic, so it doesn't get asked a lot. The idea is that if you have a function f(x,y), then if you want to find df, which is the approximation of the change in f, then df is equal to the derivative of f with respect to x times dx plus the derivative of f with respect to y times dy. The understanding that every time you say dx, it's approximately the change in x. And if you say dy, then it's the change in y. And if you say df, then it's the change in f, right? This is basically linearization. This is basically linearization. I'll tell you why. So let's say you are at point AB, right? And then you change by dx. So you just change, so x and y, x change by dx. So let's say x goes from a to a plus some change in x, and then y, it goes from b to b plus some change in y, let's say. So if we were to write linearization in this case, we would get lxy, bear with me, I'll show you how these are the same. That would be f of ab minus f sub x times x minus a, plus f sub y times y minus b. Look, if you move this here, so lxy minus f of ab, so that's the change in f. Right, fxy, lxy is the new point that you're trying to estimate, minus f of ab, which is the old point, so that's delta f. Now this is fx. Now what's the new x? Minus a, that's just dx, so the change in x. And the same thing here, it's fy times the change in y. So literally you're actually doing linearization in a different way. I'll give you a simple example. Again, this is rarely asked. So let's say we have fxy equals to x squared plus y cubed. And let's say that dx, like let's say sometimes they tell you the error on x is 0.1. So dx is 0.1. The error on y is 0.2. So what would be df? Of course, at what, let's say x is equal to 1, y is equal to 2, let's say. So what's df is equal to? Really, you just calculate the formula for df. So df is equal to the derivative with respect to x times dx plus the derivative with respect to y dy. So 2 times 1, dx is 0.1, 3y squared, dy is 0.2, and you just get 0.2 plus 12 times 0.2, so 2.4, so the difference in y is 2.6. So if the error on the x is 0.1, the error on the y is 0.2, then technically the maximum error on f is 2.6. It's not a super popular question, so I'm only dedicating this much for differentials. And now for the last bit of the on-demand part. Since we've covered everything that's on the midterm, I decided to dedicate just a little bit of time to solving extra problems from topics after the midterm. You will be able to fully understand this part after you've been to the live session, so after I've explained all of the topics for you. Right now there will be no explanation, they'll just be solving problems. The explanations would have happened in the live session and you would have seen them, sorry. So this part is just extra practice. I'll choose older finals, that stuff that we wouldn't have solved in the live session, so that would constitute extra practice for you for the topics after the midterm, which I guess you're a bit more stressed about than the stuff from the midterm, because you know, they're new stuff. Now, I picked April 2017. I figured this is enough going back that we won't actually have time to solve all of these questions in the session, because we have plenty of years after that to work with in the session. So here we go. Calculate the iterated integral by interchanging the order of integration. So as you know, we're going to write the old bounds, we're going to draw the old bounds, and then we're going to write the new bounds. So what is this? This is y going from 0 to 4. Again, there is no explanation in this part, they're just solving. The explanation would have happened in the live session. So those are the bounds for y, and now x goes between root y and 2 minus the square root of 4 minus y. So they really didn't make it easy on this one. So let's try and graph this. So when y, let's see, when x is equal to root y, x is equal to root y, that would mean y equals to x squared, so it's this. Come on. Of course there's also this part, but I have a feeling that we won't need the other side. Let's check. And then what's the other one? X is equal to 2 minus the square root of 4 minus y. So this means the square root of 4 minus y is equal to 2 minus x. So 4 minus y is equal to 2 minus x squared. So y is equal to 4 minus 2 minus x squared. Which is, if you expand it, 4 minus 4 is gone. That would be minus 4x, so 4x minus x squared. 4x minus x squared is a parabola that's upside down, like the sad face parabola. It goes through x equals to 0 and x equals to 4, 1, 2, 3, 4, and it just does this. Right. Why can't I draw this? Let's do again. Here we go. That works. So maybe it won't do as much. It would just so this one would be a little bit higher, and this one would be like this. In fact, if you draw it very nicely, you'll realize that there's this point that's y equals to 4. So when y goes from 0 to 4, so when y is here, 0 to 4, x goes from root y to x goes from root y. Oh, I wrote this the other way around. I'm sure you would have told me if this wasn't a live session, so if this wasn't a recording. So 2 minus 4 minus y, that's the lower bound, and root y is the upper bound. Sorry about that. So now it makes sense. That was what didn't make sense before. So x goes from this curve to this curve. Right? Now, we know, well, we don't know, we have to check, but they meet at 2. We can check that 2 minus the square root of 4 minus y is equal to the square root of y. And you can actually check this, right? You don't have to solve for it. You can check y equals to 4, and you know that y equals to 4 works. Y equals to 4 here, it gives you 2. Y equals to 4 here equals to 2. So y equals to 4 works, and if y equals to 4, then x is equal to 2. So we're checking for which one is the answer rather than solving for which one is the intersection, I mean. Right, so by changing the bounds, now I need to fix x. So x is fixed from 0 to 2. So my new bounds are x from 0 to 2. And y goes from here to here. So y goes, what's this curve? This is the curve y equals to x squared. And this is the curve y equals to 4x minus x squared. So y goes from x squared to 4x minus x squared. And therefore, the integral is the integral from 0 to 2 for x, the integral from x squared to 4x minus x squared. Now this is dy dx. And to evaluate it, we take the integral of y dy, which is y, from x squared to 4x minus x squared dx. This is the integral from 0 to 2 of 4x minus x squared minus x squared dx, and I'm sure you're able to finish. This is a simple integral. The integral of 4x is 2x squared. The integral of minus 2x squared is minus 2x3 over 3 from 0 to 2. So that's 4 minus 16 over 3, which is minus 4 over 3. Not 4, it's 8. Sorry. So 24 minus 16 is 8 over 3. And that's number 5, which is interchanging the order on a double integral. Let's see what else does this final hold for us. Here's another one that they ask us to go to polar coordinates. Again, one more time, there are no explanations in this part. The explanation would happen in the live session. I'm just solving extra problems for you. So let's see. Convert this integral to polar and evaluate. So we know that x is between 0 and 1 and y is between x and the square root of 2x minus x squared. Now we need to understand what these curves are. Y equals to x is a simple curve. We all understand what y equals x means. So this is y equals to x. Now how does y equals to that means? And this is one of those famous polar curves. If you take y equals to 2x minus x squared, first of all y is positive. If we square both sides, that gives us y squared is equal to 2x minus x squared. So we have x squared plus y squared is equal to 2x. And I would have mentioned this in the live session. So this is a circle centered. The center of this circle is 0, 1, and the radius of this circle is 1. Of course, once again, if you want to see it, you can complete the square. So x squared minus 2x plus y squared is equal to 0. You complete the square by doing plus 1 here and plus 1 here. So this gives you x minus 1 squared plus y squared is equal to 1. And that's what you got here. Of course, what's the equation of this in polar? If you want to go to polar, x squared plus y squared is r squared. X is r cos theta. So you simplify by r, and r is equal to 2 cosine theta. So the equation of this curve is 2 cosine theta. So how does it look? It's the circle centered at 1, 0, and of radius 1 with y positive. So that's like this. That's a circle, so it's more curvy. So it's center 1, so that would be 2. And now let's look at our region. When x goes from 0 to 1, I bet you that the 1 is where they meet. So can I make this better? Sorry, graphing is a little bit tricky, so that's a better graph maybe. So when x goes from 0 to 1, y goes from x to the other curve. So y goes in here. And I remind you, what's the equation of this curve in polar? It's r is equal to 2 cosine theta. What's y equals to x in polar, everyone? That's theta equals to pi over 4. Remember that theta is tangent inverse y over x. So how do we write the bounds in polar? Well, let's see. Theta goes from here to whenever this is 0. So where is 2 cosine theta equals to 0? Where does 2 cosine theta equals to 0? It's when cosine theta equals to 0. So when theta is equal to pi over 2. So great. It was, from pi over 4 to pi over 2. That's my theta. Now r, again, how do we find r? We start at the origin and we go through our region, and r goes from 0 to the outer bound of r. So theta is pi over 4 to pi over 2, and r goes from 0 to 2 cosine theta. Fantastic. So that's it. So we're taking the integral from pi over 4 to pi over 2, the integral from 0 to 2 cos theta of dx dy, dy dx is going to be r dr d theta. So let's evaluate this. This would be the integral from pi over 4 to pi over 2, r squared over 2, 0 to 2 cosine theta d theta. So this is pi over 4 to pi over 2. That would be 4 cosine squared, so 2 cosine squared theta d theta. They gave us the hint that 2 cosine squared is cosine 2 theta plus 1. So this is the integral from pi over 4 to pi over 2 of cosine 2 theta plus 1. Right, they gave us 2 cosine squared. You just needed to move the 1 over. So this would be sine 2 theta over 2 plus theta from pi over 4 to pi over 2. So this would be sine of pi, which is 0, plus pi over 2, minus sine of pi over 2, which is 1. So this is minus 1/2, plus pi over 4. So pi over 2 minus pi over 4 is pi over 4 minus 1/2. And that's the answer, unless I've made a calculation error. Right? So let's see. It's pretty awesome. Convert the area to polar and evaluate. So that's an excellent question. Let's see what would be next. Interpret the integral as the area of the region and use geometry. Oh, okay. Well, I didn't see that one coming. So let's see. Maybe keep it on the same page. So how could we use geometry to do this? Maybe, so we're finding the area. Okay, so it's not so bad. We think of this as the quarter of the area of the disk. So the red area, so it's the red minus the green area. Now the red area is the quarter. The red area is a quarter of pi r squared. The radius is 1, minus the green area is a triangle. So this is 1, so a half base times height. So this is pi over 4 minus 1/2. Well, what do you know? It's actually the same. So the quarter of the area of this disk minus the green area, which is a triangle. So that was fun. Okay, let's see what else. Let's do number 7. Again, there's no explanations here. We're just solving. Explanations are in the live session. So the solid E is the set of all points below the paraboloid. So below the paraboloid, above the other paraboloid, and the density is given, and the density is given to us as 2z. Find the mass. Well, the mass, the volume is the triple integral of 1. The mass is the triple integral of the density. So mass is the triple integral over the region E of the density dV, because the volume is the triple integral of 1. The mass would be the triple integral of the density. Now let's try and find out, no, I thought I had do not disturb on. Oh, they called me twice. So these frauders are now smart enough to call, hang up, and call again. So if you have it on like do not disturb, they get through to you. Anyway, so the solid E is, so we have a paraboloid like this, and we have a paraboloid like this, so we need to find where they meet, because technically that would be the range in the xy plane. We know what the range for z is. Z is going to be bounded below by, it's above this paraboloid, so it's above this, below this, so this is the range for z. And right, this is screaming polar or cylindrical, right? Because it's all x squared plus y squared. Oh, they even say u cylindrical. So, right, so what's happening for this? When these two intersect, we're gonna get this disk right here, and that's the disk over which we integrate in the xy plane, right? So this is the region in the xy plane that we use to find the range for x and y. So we know what z is. We get the range in the xy plane over which x and y live. So when we set them equal, 8 minus x squared minus y squared is equal to x squared plus y squared. We get x squared plus y squared is equal to 4. So the region in the xy plane is very much polar, if you want to draw it. So the region in the xy plane is this. It's the circle of radius 2. So this would be the region that we'd have right there. So what would be the bounds? In terms of theta, theta goes from 0 to 2 pi. In terms of r, r goes from 0 to 2. In terms of z, z goes from this, which is r squared. I remind you, x squared plus y squared is r squared, to the top one, which is 8 minus r squared, of 2z. Z is z in cylindrical. Now dx, dy, dz is going to be r dr dz dr d theta. And that gets us the mass of E. So let's carefully do this. Integral from 0 to 2 pi, integral from 0 to 2. We're integrating z now, so the integral of 2z is z squared, r from r squared to 8 minus r squared dr d theta. It's a little bit annoying to do all the calculations, but they're not hard. So this would be 8 minus r squared squared times r minus r squared squared times r dr d theta. So this is the integral from 0 to 2 pi. This is 64 minus 16r squared plus r to the 4. Multiply everything by r. So 64r minus 16r cubed plus r to the 5 minus r to the 5, so that's gone. So that would be this dr d theta. So when you integrate with respect to r, that is 32r squared minus 16r 4 over r4, so 4r to the 4 from 0 to 2. You can keep the 0 to 2 pi d theta, or you can integrate the d theta separately. But anyway, let's pretend you did this. So this would be 32 times 4. 32 times 4 minus 4 times 16. That would be 64. So that's the integral from 0 to 2 pi of 64 d theta, which is going to be 128 pi. So the mass is 128 pi, and that's a typical example of cylindrical coordinates. Next, they say give an iterated integral for z bar, the center of mass. So how do we find z bar? I remind you the formulas are very simple. So to get z bar, the center of mass would be x bar, y bar, z bar. But here, due to the how the density only varies with z, but the density only varies with z. So let's pretend let's not pretend, this is the z-axis. So the density varies with z, the density that doesn't vary with the x and y. So we expect the center of mass to be here, somewhere here. So we expect the center of mass to be 0, 0, z bar. So even if they told us to find x bar and y bar, they would be 0 because of the symmetry of the density and the symmetry of the object. So how do we find z bar? It's 1 over m. Technically, z bar in general, it's the triple integral over the region E of z density dV over mass, which is the triple integral of the density. But here we have mass. Mass is 1 over 128. So mass is 128 pi. And z bar, this would be the integral with the same bounds, 0 to 2 pi, 0 to 2, r squared to 8 minus r squared. Now we have z, and then rho is 2z, and then we have r dz dr d theta. They say give an iterated integral, so you just leave your answer like this. You don't need to continue any further. Right? So let's go to number 8. So there's 10 problems in this. Cool. So number 8. 8 is a Maclaurin series, one of my favorite topics. Let's go to a new page. It deserves a new page. So by any means find a Maclaurin series for ln 1 plus x squared. Now there's two ways we could do this. We can, if they let us memorize the series of ln 1 plus x, which is the summation from n equals 0 to infinity of minus 1 to the n x to the n plus 1 over n plus 1. So some people memorize it like this. Some people memorize it as the summation n equals 1 to infinity minus 1 to the n minus 1 x to the n over n. I'm not sure if which of those two you do. It's basically the same idea. So you just replace x by x squared. So that would be the summation from n equals 0 to infinity minus 1 to the n, x squared to the n plus 1, all divided by n plus 1, which is the summation n equals 0 to infinity minus 1 to the n, x to the 2n plus 2 over n plus 1. Now, if you aren't allowed to memorize this, so if this is not allowed in terms of memorization, here's how we do this. We say let y equals to ln of 1 plus x squared. So from the many examples that we would have done in the live session, you know that to get to the Maclaurin series of this, we need to derive. We would get 2x over 1 plus x squared. So basically this is 2x times the super famous series 1 over 1 plus x squared. One more time, what would this series, we again, I'm sure that we will talk a lot about this in the live session. So it would be this, as long as square is between minus 1 and 1. Super famous Maclaurin series, the 1 over 1 minus x. 1 over 1 minus box is the summation of box to the n, as long as box is between minus 1 and 1. So that one you definitely need to know. Ln 1 plus x maybe not, but this one you definitely have to know. So this would be 2x, and this we put in the box minus x squared, so that would be the integral from 0 to infinity minus x squared to the n. So this is 2x, the summation n equals 0 to infinity minus 1 to the n x to the 2n. Now we're going to multiply this by 2x, so this would be the summation from n equals 0 to infinity minus 1 to the n times 2x to the 2n plus 1. Right, now I don't know why I went into another line, it surely fits here. Now remember, this is y prime. What we want is y, so we integrate. What's y equal to? And we integrate only the x's, right? The other ones are constants. So this is minus 1 to the n times 2. Those are the constants. And the integral of this is x to the 2n plus 2 over 2n plus 2 plus c. You remember that c is always f at 0 when we're using Maclaurin. So here you plug f of 0 here, which would have given you ln of 1, which is 0. So there's no c. And how do I get back to the one I have before? Look, this is the summation n equals 0 to infinity minus 1 to the n, 2 times x to the 2n plus 2, no problem. But then divided here, I can factor it 2 and get 2 times n plus 1. 2 and 2 cancels out, and here you go. You end up with the exact same formula that you have before, which is the Maclaurin series of ln of 1 plus x squared. Right? Okay, let's see in part B, use the series to provide an estimate, and this is the alternating series error term. So now this was it really just doesn't want to copy. Now I didn't copy the link properly, so this is, we're gonna assume this is 0.5. So this is an alternating series error term, ln of 1 plus x squared. Of course, we still have to integrate it here, but ln of 1 plus x squared, we showed in the previous example, it's equal to this, minus 1 to the n, x to the 2n plus 2 over n plus 1. So now we're integrating this from 0 to 0.5. So we have the integral from 0 to 0.5 of the summation from n equals 0 to infinity of minus 1 to the n, x to the 2n plus 2 over n plus 1 dx. Remember, when we integrate, we just integrate the x, the constants just stay. And this is x to the 2n plus 3 over 2n plus 3 from 0 to 0.5. And then that's going to give us the summation n equals 0 to infinity minus 1 to the n, 0.5 to the 2n plus 3, all divided by n plus 1 to n plus 3. Great, so this is an alternating series, and this is an alternating series where this is bn. Right, an alternating series is minus 1 to the n bn, so this is bn. So we want the error to be less than 0.0001, 10 to the minus 4. So how do we do the alternating series estimation error? We find the bn that's less than this, and we stop before it. So we find the bn that's less than this, and we stop before it. So if we try b0 by plugging n equals to 0, that's going to be 0.5 cubed over 3. That's bigger than 0.0001. If we try b1, that would be, again, without the minus, 0.5 to the power 5 over 2 times 5. That's 0.003125, again bigger than 0.0001. You're gonna check b2. b2 is 0.5 to the 7 divided by b2, that's 3 times 7. This would be 0.000, actually let me check, I don't have that value, 0.5 to the power 7 divided by 21. So that would be, again, not enough, 0.00037, so that's not. And then b3, for sure it's going to work, that's going to be 0.5 to the power 9 divided by 4 times 9. And this is less than 0.0001. So since b3 is less than, we stop before b3. So we say that the integral from 0 to 0.5 of ln of 1 plus x squared dx is approximately equal to, right, we're going to list the terms, but now with the minus. So b0 minus b1, now you have to accommodate the minus, plus b2. So we stop at b2, and then you can write those down. So this is 0.5 to the 3 over 3 minus 0.5 to the 5 over 10 plus 0.5 to the 7 over 21, and then the error is less than the first term you leave out, so the error is less than or equal to b3, and b3 we chose it so that it's less than 10 to the minus 4, and here you go, that tells you that the error is less than 10 to the minus 4. That's alternating series approximation error. Right, so I'm going to take a super short break and I'll come back to continue with this work. So we continue with number 9. Calculate the first 5 terms of the Maclaurin series up to the x to the 4 terms. For the function, you will be calculating the degree 4 Taylor polynomial centered at 0. So let's do that. If n is equal to 0, the function is just 1 plus x to the half, and if I replace x by 0, I get 1. If n is equal to 1, n is equal to 2, n is equal to 3, and n is equal to 4. So this would be a half, excuse me, 1 plus x to the minus half. At 0, it's minus a half. This is minus a half times a half, 1 plus x to the minus 3 halves, so this is minus 1/4. Sorry, it's a half here, right? So if I put 3, then this would be 1/2 times 1/2 times 3 halves of 1 plus x to the minus 5 halves, and then that would be 3 over 8, and this one would be minus 1 times 3 times 5 over 2 to the power 4, 1 plus x to the minus 7 halves, and that would be negative 15 over 16. Calculate the first 5 terms of the Maclaurin series. That means T4 of x is equal to f of 0 plus f prime at 0 x to the power 1 plus f double prime at 0, so minus 1 over 4 divided by 2 factorial x to the 2, then plus 3 to the 8 over 3 factorial x to the 3 minus 15 over 16 over 4 factorial x to the power 4. Right? Provides a general formula for n bigger than or equal to 2. So for n bigger than or equal to 2, you could see right away that n2 is negative, n3 is positive, n4 is negative. So we have a minus 1 to the power n minus 1, n minus 1 or n plus 1. No, for n is equal to 2, we're going to get 2 to the power 2, 2 to the power 3, 2 to the power 4. So there's always on the bottom 2 to the power n. Now, of course, here we're dividing by 2 factorial, we're dividing by 3 factorial, so this is divided by n factorial. Also, don't forget that this term, this is not the term when you take fn and you divide it by n factorial. So the coefficient, right, so the coefficient of x to the n is the nth derivative at 0 divided by n factorial. And now here, for the 2 term we get 1, for 3 we get 1 times 3, for 5 we get, for 4 we get 1 times 3 times 5. So if you try this, and this takes a bit of trial and error, so it's going to be 1 times 3 times 5. Where do we stop? We stop at 2n minus 3. Look, for n is equal to 2, you get 1. 2n minus 3 is 1. For n is equal to 3, 2n minus 3 is 3. So you stop at 3. For n is equal to 4, you're going to get 2n minus 3, which is 5, and you stop at 5. Now again, how did I come up with 2n minus 3? There's several ways. I said for n is equal to 2, I stop at 1. For n is equal to 3, I stop at 3. For n is equal to 4, I stop at 5. So maybe get two points of these and find the equation of the line. So this would be the general coefficient of x to the power n. So if you want the xn term, that would be minus 1 to the n minus 1, 1 times 3 all the way till 2n minus 3 over n factorial 2 to the power n x to the n. Right, let's continue. For part, I think there was a part C. Yeah, see, part C is the error bound, and we're definitely gonna go over examples of the theory, of course, and other examples of the error bound. So use Taylor's upper bound error. So they give us the error. To give an upper bound on the error, if the degree 3 polynomial is used to estimate 1 plus x to the half in the interval minus 0.5 to 0.5. Now the first thing, the interval is centered at 0, right? The interval, the center is 0, so this is 0 minus 0.5, and then 0 plus 0.5. So the center here, it's a Maclaurin series, so it's centered at 0. So you go minus 0.5 that way, and you go 0.5 that way. So that means d, which is the distance you go either way, is 0.5. So that takes care of d. Now we stop at term 3, right? So E3, the error we get if we stop at term 3 is the upper bound on the fourth derivative at x divided by 4 factorial times 0.5 to the power 4, right? Because n is 3, so we're replacing it here. So what's the fourth derivative? The fourth derivative is minus 15 over 16. The fourth derivative at x is equal to minus 15 on 16 x plus 1 to the minus 7 halves. And this tells me these two bounds, as you probably know already from the live session, these wants the maximum amount. So this is, we want an upper bound. So we want an upper bound. So what is the maximum value that this can take when you are in the interval minus 0.5, 0.5? Okay, we don't care about the sign, right? We don't care about the sign. So what would be the maximum value that this can take when x is equal to 0.5? Again, we don't care about the sign. And because this is the divided, so this is minus 15 over 16 x plus 1 to the 7 halves. To get the maximum value of this, you would like to take x is equal to minus 0.5. See, in this interval, to make this the largest possible, again with no regards to sign, you want to get your denominator to be as small as possible. That gives you the largest fraction. So you use x equals to minus 0.5. So E3 is equal to 15 over 16, right? We agreed the sign doesn't matter. When you put minus 0.5 there, that's 0.5 to the power minus 7 halves times 0.5 to the power 4 over 4 factorial. And that, ladies and gentlemen, is the upper bound of the error. If you calculate this, then this is 0.02762. Right? So we would have done more examples of this in the live session once we do that. Continuing with this, now interchange the order of so this one is the type of questions that the students hate the most. So we're down to the last problem. Triple integrals are always not a crowd favorite because the drawings are difficult, but let's try and demystify it as much as possible. X goes from 0 to 1. Y goes from 2x to 2. While Z goes from 0 to 2 minus y. So this is on the axis, this is in the plane, this is in space. So let's attempt to draw this this object, and we want to change the bounds to these. So we wrote the old bounds, we're going to draw the old bounds, and then we're going to write the new bounds. Again, this is the part that, you know, it's a little bit annoying, but with practice you get to be better and better at this. So x goes from 0 to 1. So on the x-axis we're going from x from 0 to 1. So on the x-axis the x lives just here. Now this is y equals to 2. So 1, 2. So this is y equals to 2. How does y equals to 2x? So if x is equal to 1, y is equal to 2. If x is equal to 0, y is equal to 0. So this is y equals to 2x. This is in the xy plane. And we know that when x goes from 0 to 1, y goes from 2x to 2. So that's my region in the xy plane. Now, z goes from 0, which is the xy plane, to the plane z is equal to 2 minus y. So 2 minus y in the zy plane is this. So it's 2 right here. This is z is equal to 2 minus y. But then it's a sheet. It's going to extend, like it's a plane. It's a flat plane like this. Z is equal to 2 minus y. And then just like it's a plane that goes over all of this. So it's going to extend like this. It's going to extend like this. So technically, it's going to form a solid like this. So z goes from 0, the xy plane, to the top part of this, which is the plane z is equal to 2 minus y. And it stops at y equals to 2x. Right? So it stops, this is the side of it. It stops here with y equals to 2x. Right, so here's our solid. Maybe we write it, we put it in a different color. So there's this, there's this, there's this, this, and then this. Okay, now what order do they want us to do? They want us to do dy, dx, dz. So z is going to be the axis, y is going to be the plane, so xz, and y is going to be in space. So let's see if we can work this out. So where does z live on the z-axis? So let's draw a few lines here. So that's like this, and then this is going to go like this. Okay. So where does z live on the z-axis? So now we're looking only at the z-axis. Where does y live on the z-axis? And where does z live on the z-axis? It's from here to here. So on the z-axis, z goes from 0 to 2. Great. Now x. Now we're looking in the xz plane. Right? So I need to find the shadow of what's happening in the xz plane. And if you see it, this is what's happening in the xy plane. You're taking z is equal to 2 minus y, which is that plane. And you're taking y equals to 2x. So you're replacing the 2x in here, kind of to drop it in the xy plane. You get this, so let's pick a different color for you. You get this line right here, and this line right here is z is equal to 2 minus 2x. And you can verify that when x is 0, z is 2. When x is 1, z is 0. Like you can see this line. So this is our object, right? This is our volume. So when z goes from 0 to 2, where does x live? We're looking at the x-axis, right? We're looking at how x changes in the xz plane. Where does x change? X changes from 0 to this curve, and here x is equal to 2 minus z over 2. Right, we solve for z, or 1 minus z over 2. Now what's y doing? Now we're looking in space. What's y doing? Y starts from here to here. So it starts here on this side, which is y equals to x over 2. And it goes to this side, which is y equals to 2 minus z. So the new bounds are the integral from 0 to 2, the integral from 0 to, I'm going to write this as 1 minus z over 2, the integral of x over 2 to 2 minus z, and that's just the integral now dy dx dz. So let's see, we want to evaluate the integral, interchange the order to evaluate. So this is going to be tedious evaluation, but why not? So which one do we evaluate? Interchange the order to, and evaluate the new integral. So they want us to evaluate the new one. So the integral of y is y. The integral of dy is y from x over 2 to 2 minus z. This is dx dz. So this is the integral 0 to 2, the integral 0, 1 minus z over 2. So this is 2 minus z minus x over 2. And this is dx dz. So now I'm integrating with respect to x. This is 0 to 2. 2x minus zx minus x to the 2 over 4 from 0 to 1 minus z over 2. There's still a dz, so this is 2 times 1 minus z over 2. Let's not forget that there's an integral still. Minus z times 1 minus z over 2 minus 1 minus z over 2 squared over 4. dz. And if you're thinking, wow, this is long, well, it is, but it's not very difficult. So let's tidy up. That's 2 minus z plus z squared over 2 minus 1 over 4. That would be 2z over 2, so z, so that would be plus z over 4. And that would be minus z to that squared over 4, so z squared over 16 dz. Right? 2 minus z x squared. Am I missing anything? 1 minus z over 2. No. Y is equal to, oh sorry, I'm sorry. See, here's my mistake. This is y equals to 2x, not x over 2. I apologize. This is y equals to 2x. That's my mistake. So here it should be 2x. Oh shoot, we're gonna have to redo this, but that's okay, we do it correctly. So this would be 2x, so this would be y, so 2 minus z minus this would be 2x, so this would be just x squared, and now so this would be minus this just squared, so that would be, let's erase this, minus 1 plus z minus z squared over 4. Right, so if we tidy up this is the integral from 0 to 2. 2 minus 1 is 1 minus z plus z squared over 4 dz. And if you do this carefully, you will get 2/3. Now this is an easy z integral. Now, I'm sure they're going to ask us verify this because this is the top. Okay, so check your work. So make sure that your work is correct. So they're saying there's two ways to do this. You could either evaluate this integral and check that you got the same thing, or you can actually do the volume of this triangular pyramid or something. So what's the volume here? The volume is, it's always going to be the area of the base when we have a pyramid like this. The area of the base times the height divided by 3. They even give you this, by the way. They even 1/3 the volume of the containing cylinder. It's a solid whose volume is a cone whose volume is easily found. 1/3. Okay, so it's just 1/3 area of the base times height. So they made it really weird in giving you the formula. What's the area of the base? So this is 1/3. The area of the base is 1/2 base times height. So 1/2, and then this is 1, and this is 2. So 1/2, 1 by 2. And then the height is 2. The height is here. Z is equal to 2. So 2 and 2 canceled out, and you get 2/3, which is exactly what you got over here. So that's how you verify that your work. 1/2 area of the base times height. It's a nice solid, so we can actually find it using geometry. And that completes the 2017 test. It completes the on-demand part. Again, if I made any typos, I apologize, and if I didn't catch them, please, if you have any questions, do not hesitate to email me, and thank you very much.